cloud, cloud convective updraft to high altitudes, they can efficiently condense their nucleate and form new particles. So this is an example of how some of the most advanced measurements we have done in the recent decade has helped to close the gap between model and measurements of new particle formation, not just near the surface, but over the upper troposphere. Moving further, I want to say that the yields of SOA have a complex dependence on oxides of nitrogen. So here this is a schematic figure which shows that up to a certain value of NOx, the isoprene SOA yields increased, but then after that, as NOx is increasing further, the yields of SOA decreases. And one of the explanation for this is that if you see here, the different dots here represent the different lumped component volatilities, and when they react with multiple generations, there can be functionalization reactions which decrease their volatility, but also fragmentation reactions which increase their volatility. So increasing NOx would increase the breaking of carbon-carbon bonds or fragmentation reactions, and that could reduce the formation of SOA. But there is this complex role of radicals and NOx in multi-generational chemistry, model parameterizations of functionalization and fragmentation as a function of NOx is challenging and is not adequately represented in most models so far. So just a brief idea of what functionalization and fragmentation is. So you have a carbon backbone here, and when it is reacted with OH or ozone or other radicals, it could add the functional groups to the carbon chain. And so what happens by addition of functional groups is the molecule becomes heavier, its volatility decreases, and so it can form more SOA. But on the other hand, when you are also oxidizing this carbon chain, you could also break the carbon-carbon bond. So in this case, you end up with two smaller molecules, and each of them would have higher volatility because they are smaller. And so this fragmentation reactions would increase the SOA yield, and would decrease the SOA formation in this case. And so there is this competition between functionalization reactions and fragmentation reactions, and how it varies with oxidation and as a function of NOx, and that can change the formation of SOA in the atmosphere. So I wanted to present some real measurements which actually show that this functionalization and fragmentation happens in the real atmosphere. And this is work from Alan Goldstein's group. This was published in PNAS. This is measurements over the Southeast United States. And it shows that when you have a monoterpene, which is a carbon-10 compound, this is measured with two advanced instruments, the GC by GC instrument and the chemical ionization mass spectrometer, SIMS. And you would see that these monoterpenes can functionalize, but then also fragment. So you see a host of different compounds, so C10s, with more oxygens here, but then also C9s and C6s here, which represent C6, C7, C8, which represent the fragmented carbon backbone. And in that paper, it was shown that the fragmentation products actually increased in the real atmosphere with aging in the presence of NOx. So these are some advanced measurements with advanced instrumentations which have shown that functionalization and fragmentation happens, and NOx has a critical role to play in this multi-generational chemistry and fragmentation and functionalization of these molecules. Now I would like to present a much more cleaner example of how anthropogenic activities have changed biogenic SOA formation. And in reality, if we want to look at how much have anthropogenic activity changed biogenic SOA, we want to go in a region which does not have any influence of anthropogenic activities. And so that kind of pristine baseline is very hard to find nowadays, because most regions in the world, including some of the forested regions, have already been perturbed or influenced by anthropogenic activities or inflow or transport of anthropogenic emissions. And so the pristine baseline of natural biogenic SOA is really hard to find. And so ideally, we need to go back in time under pre-industrial conditions if we want to fully unravel how anthropogenic activities have influenced biogenic SOA formation. But there was a field campaign which was designed in the Amazon rainforest. This is just a snapshot during the Go Amazon 2014-15 field campaign where the showing the measurements with the DOE G1 aircraft. So here you could see the vast green area of the Amazon. If you look from outside, it looks like a green ocean, especially in the wet season. And then over this ocean, this is the cleanest you could get to a terrestrial region which approaches pre-industrial times. Because if we are measuring the NOx concentrations, they are at levels of parts per trillion in the wet season in the pre-industrial background in the Amazon. And this has a lone source here, the urban emissions from the Manaus urban city, which is in the center of this region here. And so ideally, if we were to fly an aircraft which goes into the plume and comes out, we will be between present day times and pre-industrial times at the same time. And so exactly that was how the Go Amazon field campaign was designed. So you see the G1 aircraft, which is flying outside the plume and inside the plume. And as it is going in the plume, you see this periodic increase in particles and gases and other things. And when it comes out in the terrestrial region, in the pre-industrial region outside of the rainforest, you see a sharp drop in gases and particles and everything else which it was measuring. And so this was a very nice opportunity to study SOA formation and anthropogenically influenced biogenic SOA. And so here we are showing measurements using the aerosol mass spectrometer, which was mounted on board the same aircraft. And the orange is measurements of organic aerosol with the AMS. And you see as the aircraft goes between pre-industrial baseline, which is around 0.5 microgram per meter cube. And once it goes into the plume, you see about a factor of 3 increase in organic aerosols here. And then we were trying to model this with WRF-Chem at high spatial resolution and with all the mechanisms we know about anthropogenic biogenic interactions of SOA. And the model predictions are shown in blue. And you could see that the model here was able to reproduce this periodic rise and fall of the aircraft as it goes out of the plume and then into the plume. And then the other thing we could do in the model is we could just turn off the Manaus urban emissions. And that is the baseline in the model with this green. So you could see if the urban emissions were not there, you would not see this increase in SOA formation in the plume. The model is predicting that about 80% of this increase, even in the plume, in the anthropogenic plume, is natural biogenic SOA. And this is because the anthropogenic emissions of oxides of nitrogen substantially increase OH radical concentrations inside the plume, and that causes much more conversion of isoprene and monoterpenes to SOA. So 80% of this is biogenic SOA, even inside the plume, but this enhancement could be achieved because of anthropogenic oxides of nitrogen. And so you see that in plume, the natural biogenic SOA was enhanced up to 300%. So this is just a summary of this finding. This was published in Nature Communications. What we see is that in the pristine wet season Amazonian rainforest background, the NOx is 20 to 50 parts per trillion, which is really, really low. But then inside the plume, the NOx is increased by a factor of 10 to 50. And so that causes increase in OH radical concentrations. And then that causes much more formation of biogenic SOA inside the plume compared to outside the plume. And you see this large increase, up to 400% increase in aerosol mass concentrations and SOA, organic aerosol mass concentrations compared to the background, which can be explained by increased biogenic SOA, but that increase is possible only by the anthropogenic emissions of oxides of nitrogen. So I want to present another example of multi-phase chemistry and organic-inorganic interactions. So one of the most important studied pathways of aqueous chemistry and multi-phase chemistry relates to isoprene epoxidiol, SOA. So once isoprene is oxidized by OH, it forms ipox gas, and this ipox gas undergoes acid-catalyzed ring opening reactions to form vitalized ring opening reactions to form with, when the particles have inorganic sulfates, they have water, they have acidity, then this ipox can from the gas phase can react with these particles and forms IPOX SOA, which comprises organosulfates and methyl tetrals. But there are, even though this is one of the well-recognized pathways and studied pathways in the last decade or so, there are still many, many unknowns to this IPOX SOA formation. And some of the key challenges is that the particle phase acidity changes as organosulfates are being formed, and also as we are forming this IPOX SOA, this coating is highly viscous, and this can reduce additional uptake of IPOX gases. Isoprene epoxydiol has been measured, SOA has been measured in many locations globally, and some of the hotspots from the measurements are over the Southeast US, over the Amazon, and some of the other regions here. But then the key, so it could contribute up to 30% to SOA formation in the Southeast US and over the Amazon. But here I want to say that key IPOX SOA processes are either not represented in many of the SOA models or are not well understood. And so this is a schematic figure from a recent paper which shows that there are key process level uncertainties like diffusion limitations in organic shell. The chemical kinetics of IPOX SOA are not well understood. And then also this kind of IPOX SOA formation can happen in the clouds, which have large volume, ample aerosol water. It could form IPOX SOA, but then when the cloud evaporates, there is cycling between clouds and aerosols. And so that is another uncertainty in terms of understanding this multi-phase chemistry of IPOX SOA and similar compounds in the real atmosphere. So how do we reduce these uncertainties? One of the ways is to use very carefully designed laboratory measurements. And here I am showing you a schematic from some measurements we did here at Pacific Northwest National Laboratory. And what was done here by my collaborators is that in a 1 meter cube Teflon chamber, ammonium bisulfate and other seeds, acidic and non-acidic seeds were injected, and then IPOX gas was injected. And once the particles are being formed, the measurements were made, not just of the size distribution, but also several other properties like the composition, the density of IPOX of the aerosol, and the volatility and evaporation kinetics as they were being formed. And so all these measurements together, the size, composition, density, and volatility, were really important to constrain the model to understand the processes happening. And measurements were made both at dry conditions and also medium relative humidity conditions. And so one of the findings from this is that a lot of the models, when IPOX SOA is getting formed, then it consumes the sulfate, the inorganic sulfate, and converts it to organosulfates. And once we are converting the inorganic sulfate to organosulfate, that causes a sharp drop in the acidity of the particle. Here it's more than two units of pH drop in acidity. And so if the models, many of the models, they don't account for this drop in acidity due to organosulfate formation. And what that does is that it could greatly overpredict the formation of IPOX SOA, because if you keep the particles acidic, even when organosulfates are getting formed, then the model will predict that you would make much more IPOX SOA compared to what actually happens here. So here you would see the black is observations, and then the red and the green are our revised model predictions, which account for this drop in particle acidity. And compared to that, this blue is a model which does not account for drop in particle acidity. So without dropping particle acidity, you could greatly overpredict IPOX SOA formation. And diffusion limitations are another aspect of this, which many models don't consider. So coming back to the part of diffusion limitations, so viscosity of organic aerosols could change in the real atmosphere. So it could vary from liquid-like, which is like water, which is free-flowing, to olive oil, honey, ketchup, peanut butter. This is viscosity is increasing in this direction, and glass marble is solid. So what that does is that if you can think of something which is liquid-like and it's taking up an organic gas, there are not much limitations, diffusion limitations for the organics to enter the particle phase and react there. But in a glass or a peanut butter, it would be much more diffusion limited. So if we can think in a semi-solid regime, in addition to diffusion limitations, the particle length scales matter. So if you have a 1 nanometer particle, an organic gas can easily reach equilibrium within a second or so, even for a semi-solid, because the diffusion length scale is very small for a 1 nanometer particle. But if you think of a 100 nanometer particle, the diffusion time scales could be a day or longer with a semi-solid. And this has implications to the uptake of organic vapors on these particles because diffusion limitations can reduce SOA formation in this case. One of the approaches to studying these diffusion limitations is taking an aqueous inorganic core which is surrounded by organic material. And so this is, we solve for diffusion and reaction within both the organic coating and the aqueous core and solve for flux balance across the interfaces. And that way we can solve for the reactive uptake of, say, IPOX gases within a coated particle. How do we predict the viscosity and diffusion limitations of SOA? So we have a framework here which was developed by Manabu and other groups, which quantify the viscosity as a function of volatility, composition, ambient temperature, and RH of the particles. So in the Amazon, for example, in the tropics, where it is warm and humid, SOA particles will be liquid-like near the surface, but as you are going higher up in the atmosphere, as the temperature is dropping and relative humidity is dropping, these particles become solid and viscosity becomes...
Dr. Manish, you have 3 more minutes.
Okay. So the viscosity has an important impact on SOA, and one of the implications of this is that when you look near the surface, there is aqueous chemistry, but when you look in the upper troposphere, what we found is that aqueous chemistry cannot happen because there is no water in the particle phase. It's the coating is solid, so the direct emissions of semi-volatile gases to the upper troposphere and their condensation in this case could explain IPOX SOA formation. So in the interest of time, I would not go further. This is another example from one of our studies where polycyclic aromatic hydrocarbons, which are cancer-causing, can be coated by viscous SOA and transport them to long distances. This is an example from cloud chemistry from one of our recent studies. And so with that, I will just leave with key takeaways that organic SOA are complex systems and the interactions with anthropogenic NOx and sulfate can modulate them. And there are several unknown processes, for example, related to surface and in-plant biochemistry, which are unaccounted sources of SOA. And then the size, number, mass, composition, optical properties, and chemistry of SOA vary around the globe, but there are critical insights to be gained from different regions, which can be brought together when we are applying it to a new region. Thank you.
Excellent talk, Dr. Manish. So we have a couple of questions. Yeah, first, Neeraj.
Hello, Dr. Manish. I am Neeraj Rastogi. First of all, thank you so much for such an interesting and informative talk. My question is related to one of the slides you were showing that isoprene SOA yield as a function of NOx. And you showed that initially it increases and after some time it decreases. So what decides that threshold that, okay, up to this point it will increase and then it will decrease? You said something that NOx is causing, carbon bond breaking. So that is why you have fragmentation and it is decreasing. But initially it is showing the increase. So that means same NOx. Yeah, so can you just explain that part?
Yeah, it's a good question. And that threshold could vary for different SOA systems. But the main idea is, like I showed an example for the Amazon rainforest, when you go from very, very small levels of NOx, like parts per trillion levels, to 1 or 2 parts per billion levels, initially the NOx will increase the OH radicals. And that could cause an increase in SOA formation. But then at some point, as you keep increasing the NOx, it will cause breaking of carbon-carbon bonds. So these are peroxy radical reactions with each other, and it could vary a lot for different SOA systems. So the specific example which I was showing was for isoprene SOA, but that kind of threshold for different like monoterpene SOA and other things still needs to be studied. And we know for Southeast US, I showed another example where monoterpene SOA also was showing fragmentation with increasing NOx. but Southeast US already represents an urban environment where NOx was already high. So yeah, I see your point, and that needs to be studied more. Thank you.
I have a couple of questions. Quickly I'll ask. So in addition to Neeraj Rastogi's question, so you have shown one aircraft observations going out from the plume and going inside to the plume. So in that plume, it is already like highly NOx reached. Like you told that it is increasing like 10 to 50 folds from 50 ppt to its 10 to 50 folds.
1 ppb.
So why?
To 1 ppb, yeah.
To 1 pp. Okay, 1 ppb. So it is
Yes.
within the threshold limit, right? So my
Yes,
question
1
was that.
ppb for many of the smog chamber measurements, 1 ppb is still classified as low NOx.
No, no.
So
Okay.
that was the whole point, that if you look at the baseline of the Amazon rainforest, the real baseline would be much, much lower than what we measure now with smog chambers and what we classify as low NOx. So even in the plume, 1 ppb, in the plume in the Amazon could still be low NOx conditions from today's chamber studies.
Okay, okay. Another question is that in one of your chamber experiments, you used ammonium bisulfate. So what is the advantage of using ammonium bisulfate instead of ammonium sulfate? Because epoxy-OAs are known to be acidic, and ammonium bisulfate also has acidic like component. It's a like single H plus ion acidic. So why, like what is the advantage in that?
Yeah, so the main thing is we wanted to do both dry experiments and wet experiments, and ammonium bisulfate does not have, I mean, it doesn't effloresce till very, very low relative humidity. So even at 5% relative humidity, it has some particle water. And so in that case, you could, it is highly acidic though, at that condition. And so we could study the effect of both relative humidity and acidity by using ammonium bisulfate seeds. But there were also experiments with ammonium sulfate, which helps you contrast the role of more acidic to less acidic particles,
Okay.
and the role of relative humidity.
Okay.
And so we do find that acidity has a strong impact on, say, oligomer formation of IPOX SOA. I didn't have time to go into further details, but we have looked at both ammonium bisulfate and ammonium sulfate. And the main advantage of ammonium bisulfate is it can retain particle water up to very, very low relative humidity.
Okay, for heterogeneous phase reactions. Okay.
Yes.
And also, like you have shown one like a model estimation of epox SOA. So which model you have utilized for predicting?
We developed this model in-house. It uses the dynamic gas part. It uses the dynamic inorganic aerosol thermodynamics, the mosaic model, and then it has box. And then we developed our own capabilities for formation of IPOX SOA, which includes many, many processes: organosulfate formation, the decrease of acidity with organosulfates, the formation of semi-volatile tetrals, in addition to organosulfates, oligomerization of tetrals. So we considered many, many processes in that box model which we developed for IPOX SOA, and we were comparing it with laboratory data of many, many things at the same time: volatility, density, size distribution evolution, the volume growth. And when we have so many things measured together, then that really helped to constrain many, many unknown parameters in the model.
Okay. And the input is isoprene and isoprene derived products, or just isoprene?
In the lab experiments, we were directly injecting IPOX in the gas phase to the seeds.
Okay.
Yes.
Okay, sir. Thank you, sir.
Thank you.
In the interest of time, so we can stop here, and let's thank Dr. Manish Joshi for an interesting
Thank you.
lecture and interactions. Thank you, Dr. Manish. Thanks.
Thank you.
So next we will move on to the next speaker, Dr. Andrew Lambe. So he'll be talking on the measurements of secondary organic aerosols using an oxidation flow reactor. So it's an invited lecture, and the time is 20 minutes. Dr. Andrew?
Thank you for the introduction. Can you hear me okay?
Yeah, please go ahead. Yeah.
Great. Thank you.
Thank you.
So thank you everyone for coming to listen to my talk today. And I'll be talking about a comparison of SOA generated from the oxidation of laboratory biogenic and anthropogenic precursors by the oxidation of OH, chlorine atoms, and bromine atoms in an OFR. And so I'd like to start by acknowledging my co-authors on this work, as well as funding from the National Science Foundation, the NANO 2023 committee for giving me the opportunity to present today, Tescorn, our distributor in India. I'm a principal research scientist at Aerosol Research Incorporated in the United States. So I'd also like to acknowledge our customers and research collaborators whose measurements with our instruments have provided insight into air quality and source apportionment efforts within India. So in that context, I thought, what better way to introduce my talk than by showing AMS measurements in and around India that are summarized in this recent paper by Gunt et al., shown here. And so this figure shows pie charts of the speciated non-refractory particulate matter measured by the AMS, broken down into its main subspecies being chloride, sulfate, nitrate, ammonium, and organics. And to me, there are three major take-home points that are apparent from this paper. One is the relatively high loadings of non-refractory particulate matter, measured at almost all of these sites, approaching hundreds of microgram per cubic meter during the winter. The organics are the green fraction of this pie chart in all of these plots, and so there's a high organic content, and depending on the season and the source region, this can be both significant contributions from primary as well as secondary organic aerosol. And then finally, something that as far as I know is relatively unique to India is the high fraction of particulate chloride. So that's the purple slices in these pie charts. And my best guess is that this is likely some indication of an important influence of halogen chemistry in these source regions, right? Because if you have enough gas phase ammonia and gas phase HCl to make ammonium chloride, which is presumably at least some significant fraction of this particular chloride, the presence of those high HCl along with other reactive chlorine species in principle should allow for significant formation of chlorine atoms as well, which are a very reactive oxidant that can compete with OH for the oxidation of many VOCs. And that's a point that I'll get to over the course of the remaining slides in my talk. Here is a summary figure from a modeling study that was recently done by Lee et al., where they investigated the influence of halogens on haze pollution in the wintertime in northern China. And some of the main points that were apparent from this modeling study is one, that both anthropogenic chlorine and bromine emissions in China, when included in this model, enhanced the PM2.5 concentrations on a study average basis by about 20%. And then within that segregation of different compound classes of PM2.5, the enhancement in SOA was even more significant, over 100% enhancement when chlorine and bromine chemistry is included in their model. And both of them were important, as was determined from this sensitivity study when they removed chlorine and removed bromine emissions separately from the model. The SOA concentrations increased from 6 to 15 microgram per cubic meter just by adding that chemistry in. And so that begged the question to me, to what extent is this representative of other source regions? And again, I would argue, looking at those chloride aerosol concentrations in and around India and comparing them to the minuscule fractions of chloride aerosol that were measured and modeled in China, it doesn't seem like that big of a leap of faith to me to imagine that halogen chemistry is probably important in India also. But with that context, I want to introduce the motivating question for this research, which is how does the chemical composition and the yield of SOA compare when it's initiated by halogen atoms versus OH oxidation, which on a global scale is the most important daytime oxidant in the atmosphere. And so to investigate this question, we conducted a series of laboratory oxidation flow reactor studies in which we continuously input biogenic or anthropogenic VOCs that were oxidized by they were oxidized in the OFR following controlled exposure to OH or chlorine atoms or bromine atoms in separate experiments. And so in this context, an OFR is best thought of as a lower cost, higher oxidation capacity smog chamber that also happens to be field deployable. And so in principle, it can be used to investigate the SOA formation potential of ambient air masses in different source regions as well. And that's an active area of research for this method. the fundamental goal of an OFR is to mimic aging timescales in the atmosphere on the order of days within a couple of minutes of residence time in the OFR in real time. And so in these experiments, that involves characterizing the number concentration and the size information of the SOA particles that were generated with a scaling mobility particle sizer and our aerosol mass spectrometer to infer the chemical composition of the SOA and calculate hydrogen to carbon ratio and oxygen to carbon ratio as measurable surrogates for the oxidation state of the SOA. So now I'm going to show results for several biogenic and anthropogenic precursors over the next few slides, and I'll start with isoprene SOAs as a canonical example to illustrate you to the type of results that we obtained. And so isoprene is a C5 biogenic VOC with 2 double bonds that happen to make it very reactive to not only OH, but also chlorine and bromine, which can directly add to both of those double bonds. And so this figure shows the SOA mass yield obtained from OH, chlorine, and bromine oxidation of isoprene across separate experiments as a function of the integrated exposure in the OFR. And so to orient you toward these numbers, 10 to the 11 per cubic centimeter of OH exposure, which is about in the mid-range of this plot on the x-axis, is about 1 day of atmospheric aging at a typical OH concentration of 10 to the 6 per cubic centimeter. Chlorine is 10 to 100 times more reactive than OH towards most VOCs. In the case of isoprene, it's about 7 times more reactive towards chlorine than it is OH. So lower exposures are needed, in principle, to obtain SOA formation. And bromine and OH have similar reactivity towards alkenes. In this case, the bromine reactivity towards isoprene is about 70% of OH. So in principle, the same numerical oxidant exposure when bromine is the oxidant should give a comparable extent of oxidation as does OH. So with that background, some of the results that we observed are as follows. We observe a maximum mass yield with isoprene of about 40% after about 1 day of equivalent atmospheric aging. We see increases in the yield of SOA at low OH exposure, followed by a decrease at higher OH exposure, and in the case of the halogens, chlorine exposure as well. As Manish discussed in his talk, this is our interpretation of this trend is the transition from a functionalization-dominated mechanism at lower exposures towards fragmentation at higher exposures, resulting in carbon loss, even as oxygen-containing functional groups are still added. And so, whereas a maximum mass yield of approaching 40% for isoprene is observed, and again, this is with no added NOx, so this is an upper limit to what the yield would be in ambient conditions. The maximum mass yield obtained with chlorine was about half of that, about 20%. And then with bromine, the yield was on the order of 1 or 2%. And as far as I know, no one has measured yields obtained from bromine oxidation of VOCs before. So while this wasn't necessarily an interesting result, it was a novel result. And then taking the same data and looking at the chemical composition of the SOA and how they evolve with aging, this figure shows the hydrogen to carbon ratio as a function of the oxygen to carbon ratio for these different isoprene SOA types. And what's apparent from this is that there's evidence of significant multi-generational oxidative aging of OH SOA and chlorine SOA, because the oxygen to carbon ratio increases from about 0.3 at the lowest OH and chlorine exposures at which we observed SOA formation, up to about 0.6 for chlorine and almost 1 for OH. Conversely, with bromine, the oxygen to carbon ratio never gets higher than about 0.3. We interpret this to be the case that even though, in principle, the extent of oxidation is similar, based on the relative reactivity of bromine and OH towards isoprene, the reactivity of bromine towards first or second generation oxidation products must be small, because if it was significant, then you would in principle see an increase in O to C ratio to a much greater extent than what's observed here. So now a similar set of results for alpha-pinene. We see the same qualitative trends in SOA yields as a function of oxygen exposure. Yields increase and then decrease significantly for alpha-pinene chlorine SOA and alpha-pinene OH SOA. But here, Again, in the absence of added NOx, the yield is higher when chlorine is the oxidant, with a maximum yield of about 45%, compared to 30% for OH at about a day of equivalent atmospheric agent. And again, bromine doesn't appear to initiate significant SOA formation with this precursor, because following the initial bromine addition to the double bond, its apparent reactivity towards later generation oxidation products seems to be small, because if it were significant, in principle, functionalization would continue when you would have increase in yield and an increase in the oxidation state of the SOA also. But again, as was observed with isoprene, the oxygen to carbon ratio of bromine SOA never gets more than 0.3 or so, whereas the O to C ratio of alpha pinene OH SOA and chlorine SOA approaches 1, along with a concurrent decrease in the H to C ratio. Toluene was one of 3 anthropogenic precursors that we examined in this study, and so I'm showing that one first. It is not reactive towards bromine on any scale, to any extent that would be applicable to atmospheric chemistries. So here we just looked at OH and chlorine. And so what was most interesting to me about this system was that we observed similar maximum mass yields regardless of whether OH or chlorine was the initiated oxidant, despite radically different changes in the elemental composition between the different oxidants. So within the experimental uncertainty, we observed yields on the order of 0.5 to 0.6, and yet the hydrogen to carbon ratio was systematically much higher in the OH SOA than the chlorine SOA. And we attribute this to just the different initial attack on the aromatic backbone of toluene by OH versus chlorine. OH adds directly to the aromatic ring, so it can create hydroxyl groups. If there's HO2 present, which there is, you could in principle form organic peroxides as well. Whereas chlorine does not add directly to the aromatic backbone. It preferentially reacts with the methyl group that's attached to it. And so we attribute that to the main reason why the H to C ratio is lower, because we're not adding alcohols, which don't result in a net decrease in H to C ratio compared to other functional groups. Contrast that now with another anthropogenic precursor, endodecane, where the elemental composition is almost exactly the same regardless of the oxidant, as you can see from how the H to C and O to C evolve on the same trend line here. The yields are different. Here, when chlorine is the oxidant, the maximum yield was higher than 2, so it's a very efficient SOA precursor. And with OH, which it's still high SOA yields approaching 1, is significantly lower than when chlorine was the oxidant. So significant dependence of the oxidant on the yield, even though the chemical composition is basically the same, at least as is inferred from the elemental ratios, because hydrogen abstraction is the dominant mechanism, whether OH or chlorine is the oxidant, since dodecane is a saturated molecule without any double bonds to add to. And then finally, this was the most interesting of all the precursors that we studied, to the point that we published a separate paper just on this one, decamethyl cyclopentasiloxane, or D5, which we use as a surrogate precursor for personal care products, was an extremely efficient SOA precursor regardless of oxidant. We saw mass yields approaching 1.5 when OH was the oxidant, similar mass yields when chlorine was the oxidant under humid conditions, where the relative humidity in the OFR is about 40%. And then in the absence of any added humidity, the mass yield under dry conditions approached 3. So a factor of 2 change in the maximum yield was observed, depending on the humidity that was used. And then related to that, excuse me, before I even get into the elemental composition of the SOA, the other point is that whereas with all of the other precursors we saw evidence of fragmentation at the highest oxygen exposures that were used, with D5 we didn't see that. The yield just keeps increasing and then or levels off. Part of that is kinetic limitations with OH, because D5 has an OH lifetime of about 10 days under typical atmospheric conditions. So maybe there just isn't enough exposure. But even when you're approaching 100 days of equivalent OH exposure, you don't see that turnover in the yield curve like you do with the other precursors. So my interpretation of this result is that the siloxane backbone that's present in D5, the silicon atoms bonded to the oxygen atoms, retain low volatility nature of SOA products, even when the methyl groups that are attached to each of the silicon atoms are functionalized or fragmented to reduce the carbon number of average carbon number of the SOA. Okay, and so now just looking at the elemental composition of the SOA and how it evolves with aging, you again see that because hydrogen abstraction is the dominant reaction pathway for D5, whether it's OH or chlorine, the H to C and the O to C ratios evolve in basically an identical fashion in a Van Creveld diagram, whereas the H to C and O to C ratio behaves very differently when there's no humidity added to the OFR. The O to C ratio approaches 2, and the hydrogen to carbon ratio drops significantly. And so we discuss some hypotheses to explain this apparent humidity dependence in the paper in more detail, but basically we think it's related to direct reaction of water vapor with alkoxy radicals that are formed following OH or chlorine attack of the D5. So to close the presentation, over the next couple of slides, I want to use our results to suggest some possible mass spectral markers to look for in ambient data with AMS measurements in terms of fragments chlorine-containing fragments that are present in all of the chlorine SOA types and then the bromine SOA types on the next slide. In the types of chlorine SOA that we sampled with the AMS, these are the chlorine-containing ions that we detected, which range from less than 1% of all of the SOA signal for dodecane to about 11% for isoprene. Cl plus and HCl plus were the dominant ions in all of these SOA systems, but there was also a series of carbon, hydrogen, and oxygen and chlorine-containing ion fragments in each of them as well, some of which were the same across all of the precursors, and others, such as C4H6Cl and C3H2ClO, were unique to toluene SOA. So in principle, these could be used to fingerprint organic chlorides in ambient AMS measurements, given enough signal. And then analogous to that, for the bromine SOA types that we characterized in this work, here are AMS measurements of bromine-containing ions in these experiments. And again, the Br plus and HBr plus ions were the largest fragments in the spectra, but then also an extensive series of carbon, hydrogen, oxygen, and bromine-containing ions were detected out to about mass discharge 200.
Dr. Andrew, you have 2 minutes more.
Great. And so in these systems, the bromine-containing ions fractions contributed about 4% to 12% of the total SOA mass. And so again, in principle, could be used to fingerprint organic bromides in ambient AMS measurements, given enough signal. So in closing, to summarize the main points of this talk, we saw that for each of the 5 SOA precursors we looked at, there were distinct yields, both in their absolute and relative values, whether OH, chlorine, or bromine was the initiating oxidant. With that said, there is much higher similarity when OH and chlorine were the oxidants than when bromine was, because OH and chlorine initiate multiple generations of oxidative aging, whereas bromine appears to be limited to 1 or 2 generations at most. And then finally, our results suggest that in source regions with active halogen chemistry, chlorine may significantly enhance the SOA formation potential in those regions, whereas bromine may not, at least not directly, because it doesn't seem to initiate significant SOA formation by itself. Any influence that it has would probably be to increase SOA formation by increasing concentrations of OH through radical recycling reactions. And so with that, if you're interested in more details from the work that I presented, I'll refer you to these publications from our group. Otherwise, be happy to take any questions. Thank you.
Thank you, Dr. Andrew, for keeping up the time and excellent talk. We can take some few questions.
Yeah.
Thank you, Dr. Lambe. Means I am Neeraj Rastogi. Thank you for the nice talk. Means in initial slides you were showing this isoprene SOA and alpha-pinene SOA. Can you go to that slide if you don't mind?
Yes. Sorry, let me.
So initially, means alpha-pinene SOA and isoprene SOA you were showing, right?
Yep. Let me go back to that. Sorry.
Yeah. Yes. Okay. So, yeah. So this right-hand side figure, that's H by C, O by C. So if you have reactant isoprene only, so to start with, how you will have any O by C, and then means for halogen, how this O by C is increasing. Means H by C decreasing, that I understand. You are replacing hydrogen by chlorine, but how O by C is increasing in this? And similar case you have shown in subsequent slides also. So can you just explain this part?
So you're asking how do you start with?
Yeah, one thing is you don't have any O by means O in this, right? If you are taking these only as a reactant, to start with there is no oxygen. Means this your isoprene has no oxygen. You have only H by C. But you are starting somewhere around 0.2, and then it is increasing with the, H by C decrease is understandable, but O by C, why it is increasing for the case of chlorine?
So I think your question is why are there no data with oxygen to carbon ratios between 0 and 0.3?
That is one thing, and other thing is the slope what you are showing here, right? So that slope means you are replacing H by either O or by Cl, right?
Right.
That is how it is evolving, right?
Mm-hmm. Yes.
But if you are doing this chemistry with halogen, how O by C is increasing? That is what one thing I would like to understand. And other thing, to start with, you are having some O. So this bromine, it is, see, in case of bromine, it is at one place.
Right.
In hydroxyradical, it is again clear that if you are oxidizing, you are putting more and more oxygen, so it is following that slope. That is understandable. I am just not able to follow this chlorine. Right.
So when chlorine or bromine initiates the oxidation of the VOCs, there is, for an alkene precursor like isoprene, they add directly to the double bond, and then the oxygen adds quickly as well to make a peroxy radical. So the chlorine or bromine addition does not prevent oxygen addition as well, in the same way that it does OH. So when OH adds the double bond, you have an alkyl radical as well, and then rapid O2 addition to make a peroxy radical, and then the fate of the peroxy radical is what influences the product distribution. Same thing for chlorine and bromine. The chlorine or the bromine itself doesn't have any oxygen, but they add to the double bond to make an alkyl radical, and then with the oxygen that's already present in ambient air or in laboratory air or whatever, that adds to make a peroxy radical, and again, from there, the fate of the peroxy radical governs the composition of the SOA.
That means when you say halogen, you are not talking about pure halogen, it is halogen oxides also.
Even when the halogen initiates the oxidation, as long as there's oxygen present, the oxygen will add to the alkyl radical containing the chlorine or bromine to make a peroxy radical that has two oxygens, at least two oxygens. And then auto-oxidation or multiple generations of oxidation will continue adding oxygen-containing functional groups to the molecule.
Okay, thanks.
Hello. Hi, Andy. Yep. This is Subrata. I have one question for you. If whatever oxidations you have shown for isoprene, monoterpene, and other species, so it is mostly homogeneous nucleation and followed by SOS, right? That path.
In these experiments, yes, any SOA formation is achieved from homogeneous nucleation.
Yes. So, my question is, if we want to add some seed particles like ammonium nitrate or something, and do the same experiments, do you have any reference for that, or if you have done that earlier?
In these experiments, we did not add seed particles. In the paper, we compared yield measurements obtained in the University of Texas Environmental Chamber, where they did use seed particles in all of their experiments. And there was not any systematic effect of seed particles for the precursors we compared, but that doesn't mean that it wouldn't have an effect under some of these experimental conditions. My guess, and it's just a guess, mind you, but my guess is that if there was any influence of condensation sink on the yields, it would perhaps be for those species or those oxidants where the yield is relatively small, because that might imply that the oxidation products were semi-volatile and might be more sensitive to changes in the condensation sink from adding seed particles. So isoprene bromine, for example, the yield might increase relatively more when you have seed particles present than when you are using isoprene OH or isoprene chlorine, where you get significant SOA formation even without adding seeds.
Because
that is a hypothesis that could be tested in future work for sure.
okay, because in real atmosphere you won't have like homogeneous like nucleation very often, so you will be always having some seed particles like black carbon or ammonium sulfate. So where the deposition will happen. So that's why my question is like, and it is doable with PAM, right?
It is, yes.
Okay.
Yeah.
Thank you. Thank you.
Okay. Thank you, Dr. Andrew, for excellent presentation and interactions. So with this, we'll go to next talk by Professor Neeraj Rastogi. So he'll be talking on the oxidative potential of atmospheric aerosols over India. I think there is a typo in this program timings. Yeah.
Yeah, thank you, Dr. Andrew and Dr. Manish. So we'll sign off now. Yeah, excellent. Yeah, thank you. Bye-bye.
So, good morning everyone. Firstly, I should thank the organizer, Dr. Vijay Ganawade and Dr. Rakesh Huda, for giving me this opportunity to share whatever little bit I know about the topic. Once you see the title, Oxidative Potential of Atmospheric Aerosol over India, many of you, including myself, will think that this belongs to the last session, Aerosol and Health. So why you are presenting it here? Are you leaving early? No, I am not leaving early. So there is some link. Let me show that. Okay. So we are hearing since yesterday. We all know that our atmosphere, it is like a cooking pan, right? It cooks whatever you are putting into it. So means you are putting primary particles directly from different sources. You are putting precursors of secondary aerosols, and all these things from different sources. We understand this part. Secondary particles are found under, means if your meteorological conditions are favorable, you form secondary particles. That also we are hearing since yesterday. We understand this part. During transport, once, whether it is from primary or secondary, once it is in the atmosphere, during transport, both primary and secondary particles can undergo a variety of physicochemical transformations, process which is called cooking or aging or atmospheric processing, whatever you want to call it, before they get removed from the atmosphere. So some example, for example, suppose you form some acidic species like sulfuric acid, nitric acid, okay? They can react with dust or sea salt, and then their physicochemical properties will change. I will just show you example of this from my earlier studies. Acid deterioration by mineral dust and sea salts. So suppose you have mineral dust, which is represented as calcium carbonate, and then you have sulfuric acid or nitric acid, and they are reacting. So it will form calcium sulfate or calcium nitrate. We know that mineral dust is coarse particle. We also know that freshly formed sulfuric acid, nitric acid are very fine particle. If they are reacting, they are forming means obviously they will form coarse particle. But what is the implication of this process? You are increasing the solubility. Dust itself is sparingly soluble, less soluble. But if you are doing this kind of processing, you are making it more soluble. Other thing, dust is hydrophobic in nature. It doesn't love water. But if you have this kind of coating at the surface, then it will attack water. So you are making the surface hydrophilic. Then you are decreasing the number concentration of fine particles. So you know, means when you are reacting one dust particle, it will react thousands of small particles. So in a way, you are changing the size distribution of those fine particles into coarse particles. And obviously, it will result in shorter resistance time of those fine particles. So we actually observed this. So this is from my thesis actually. And you see, there is an anti-correlation between EA upon calcium and bicarbonate upon calcium. So what does that mean? So let me first tell what is EA. EA is excess acid, which is Ta minus ammonium plus potassium. And now what is Ta? Is total acid. And SS means non-sea salt sulfate plus nitrate. So we calculated total acid. Now part of it which is already balanced by ammonium potassium, we remove. So that is excess acid. Now if this is reacting with calcium carbonate, you are supposed to get anti-correlation. And that is what we got around the year for 2001 and 2002. So that means we have shown that these reactions are actually happening over Ahmedabad. Same thing if you are going to sea. We have sea salts. They can react with sulfuric acid, they can react with nitric acid also, and they will form sodium sulfate or sodium nitrate, and you will release HCl. But how do you know this reaction is happening? So this is the, from multiple cruises over northern Indian Ocean, I am saying it is mainly Bay of Bengal. Multiple cruises, usually from 2000 to 2009, multiple cruises, and the relationship is chloride deficit versus excess sulfate. Now what is chloride deficit? Means we know that chloride by sodium ratio in sea salt is 1.8. So that means expected chloride is 1.8 times sodium concentration. So this is expected chloride, but this is what we measured. So whatever difference is here, that is deficit. So if there is deficit, we have seen that chloride deficit and excess sulfate was correlating very well. That means these reactions were happening over the marine atmospheric boundary layer. And implication of that, just in previous talk we heard, you are releasing the HCl. So okay, let us see what is. So what we told here, that near quantitative chloride depletion was observed. Near quantitative means almost all chloride has gone. Very small amount of chloride we were able to measure. The deficit was very high, which also means that sea salt could serve as a potential sink for anthropogenic SO2 in the dominant polluted marine environment. And this loss of HCl, what was talked in the previous talk also, that it can be large source of reactive chlorine that has implication to oxidant chemistry in the marine atmospheric boundary layer. Okay, so what we understood? Okay, so what we understood so far? That aerosol aging can modify the size, composition, and surface properties of aerosol. What else it can do? So if you have acidic species, they can also affect the abundance of soluble metals. Now what does that mean? Say if you have some dust, it will have some iron also. That iron, if you are simply putting in water, that concentration will be very low. But if it is with acidic species, then soluble iron will increase. And what is the implication of that? It will change the bioavailability of micronutrients. So whomsoever is working on surface ocean, iron is a micronutrient. So if it is reacting, dust is reacting with acidic species, for the same amount of mineral dust deposition, you are adding more soluble iron. So that is another thing. Okay. So other than that, redox active metals can generate reactive oxidation species. What is that? That we'll be talking in the next slide. Through Fenton and Haber-Weiss type of reactions. After that, in addition, organics like PHs, they are oxidized to their derivatives like quinones. They are redox active. They can also generate reactive oxidation species. Further, upon deliquescence or during cloud or fog processing of SOA, decomposition of organic hydroperoxide, that can also generate reactive oxidation species. So by any means, if you are generating more ROS in the atmosphere, that would increase the oxidizing capacity of the atmosphere. and facilitate the SOA formation or their rapid aging. So in 2 slides, whatever I said, this is the summary. Aerosol aging causes various types of chemical transformation, and presence of organic, inorganic, greenhouse active species can generate ROS and may affect the oxidizing capacity of atmosphere. Okay, now what is ROS and oxidative potential, where we are talking now. So in a sequential univalent reduction process, this oxygen undergoes reduction forming several reactive intermediates. So oxygen, if it is getting electron from somewhere, it will form superoxide anion, then hydrogen peroxide, hydroxy radical, and ultimately water. From where this electron is coming? This electron is given by the redox active species present in aerosols. This ROS can be radicals like superoxide, hydroxyl, peroxyl, alkoxyl, hydroperoxyl radicals, or they can be non-radicals also like hydrogen peroxide, hypochlorous acid, ozone, singlet oxygen, peroxydated and all. So now what is oxidative potential? Ability of ambient aerosol to generate ROS or deplete antioxidant. Deplete antioxidant is only related to health inside our body. Depleting antioxidant or generating ROS, kind of similar. But when we are talking about atmosphere, capacity of aerosol to generate ROS is called their oxidative potential. Now redox active species, what I am saying, they can, means any species which can give or take electron, they are redox active. In inorganics, we know all transition elements are like that, like iron, manganese, copper, cobalt, chromium, molybdenum, nickel, etc. And in organics, like derivatives of pHs, quinones, they can be this redox active. So ROS present anywhere. If it is in ambient air, they form via photochemistry through multiphase reactions and affect atmospheric oxidizing capacity and secondary organic aerosol formation. In human body, they form via intracellular metabolism and cytosolic enzymes, and they cause oxidative stress, inflammation, cell death, which lead to various cardiopulmonary diseases. In plants, they form due to sunlight intensity, or salinity, drought, nutrient deficiency, pathogen attack, and they affect the productivity of the growth. So in short, ROS, wherever they are affecting inside our body, in plants or atmosphere. Now I will be talking what we have done. So with the thesis of my student Anil Patel, means we were lucky that we started this aerosol oxidative potential work in India. You see these red dots, these are the places from where he collected the samples. Port Blair, Shillong, Patiala, Kanpur, Mount Abu, Ahmedabad, and then there was a cruise over Arabian Sea. So all these places we collected the samples. And then we did variety of chemical speciation, like major ions, TOC, acid soluble metals, water soluble metals, brown carbon, this water soluble organic aerosol through offline AMS, and oxidative potential through DTT method. Now let me briefly tell what is DTT method. So aerosol oxidative potential through DTT method. So what you do in this case, you take some thiazolidinol, 100 micromolar you take in different vials. You take, this is very laborious work. You said 5 vials you take. In each case you are taking 100 micromolar of DTT. Now you are adding soluble PM in all. PM start consuming that DTT. Now in different vials you are adding this DTMB at different times. So first vial you are putting 10 minutes, second vial you are putting 20 minutes, 30 minutes, 40 minutes, like that. And then you are measuring the remaining DTT. Once you put DTMB, it quenches the reaction, so it stops. So whatever remaining DTT is there, that is what you are measuring. So as a function of time, it decreases. So from sample to sample you will see the slopes are different. Steeper the slope means higher the oxidative potential. Okay, so actually this slope is by micromole per minute. That is oxidative potential, which you call DTT activity also, or oxidative potential, or consumption rate of DTT. Now you have measured this. Now if you normalize it with respect to the volume of air you collected, you call it OPV. If you normalize it with respect to mass of aerosol collected, you call it OPM. So per unit mass is OPM, per unit volume of air is OPV. This is what, okay? Now, this is what we have observed over Patiala. So what do you see here? OPV versus PM2.5 and OPM versus PM2.5. We see there is a significant correlation. There was a scatter, but there was a significant correlation between OPV and PM2.5. But if you see OPM, for similar mass concentration, it is ranging from here to here. Mass concentration is the same, but OPM is varying too much. So what could be the reason for that? So actually, if you see OPV, you can write like this. OPV is equal to OPM into PM. The slope of that line is OPM. If you divide OPV by microgram per meter cube, it will come OP per microgram, right? So what is happening? Why it is showing like this? If that line is very tight correlation, say R square is 1. So here you will see a flat line. Because this is per unit mass. Why should vary per unit mass, right? Per unit mass should remain flat. It is independent of mass concentration, but it is varying. So why? Let us try to understand a little bit of that. Say, suppose this red portion is your PM mass, and that black dot what I am showing is redox active species present in that mass. And this arrow is OPM. OPM. Huh? Now, if we change that in the same proportion, whether increase or decrease, same proportion. So whatever percentage you are increasing redox active, same amount you are increasing this mass, or reducing the same proportion, OPM will remain same. Okay? But if suppose if you increase the mass and your redox active species are similar, OPM will decrease. Right? Again, if you keep the mass same, but redox active species should decrease, OPM will decrease. Again, mass is same, but redox active species are more, OPM will increase. So that is, for example, this case maybe for this kind of sample. This case, you see, high concentration is too high, but OPM is low. So this kind of example. Okay. So in short, what I am saying here, that OPM depends upon the chemical composition, that is relative abundance of redox active species in particulate matter. Okay. Now some results, let us see. So this is the study we did over Delhi. This was online RS measurement, and it was done from post-monsoon to winter. And what we saw, that traffic was mostly contributing to OPV. In Diwali, obviously, it was fireworks, and during winter, it was biomass burning. But in all the season, secondary aerosols and atmospheric processing, it was affecting OPV. This was another study which was compared Delhi versus Illinois. Mass concentration, you see, mass concentration over Delhi was 13 times higher than Illinois. But once you compared OPV, it was only 5 times. Reason is same what we discussed in previous slide. It is the redox active species which are present in, now irrespective of the total mass concentration. So that means in Illinois, redox active species are higher. That is why you are getting similar OPV compared to mass. Okay. Then some correlation. What we saw, that OPM showed a very significant relationship with MBZ 44, which is a representative of oxidized organic aerosol. And then also with this C2 formaldehyde group greater than 1, and with potassium, which is a proxy of biomass burning, and with sulfate. So simply one would infer that these species are responsible for the observed OPM, or sources emitting these species also emit redox active species responsible for observed OPM. Why I am adding the second line? Because over Patiala, in previous slide I showed there is a good correlation with sulfate. Over Patiala we have shown that with SIA it is negative trend, OP. So we observed the negative correlation between SIA and OPV over Patiala. And to investigate that further, we did some lab experiment, and we found a negative correlation. So to investigate here, so we found that SIA is DTT inactive. Now again recall that whatever red dot versus black I was showing. So in that case, even if your redox active species is remaining same, and inactive species you are adding more, so OPM will decrease. It will appear to decrease. So that is what we observe. So it means that, so now this we understand. So it means that mere correlation between opium and major species does not allow one to infer that a species is responsible for opium. We need to understand the underlying mechanism. And we need more detailed studies with spatiotemporal coverage along with aerosol OP, along with size, composition and meteorological factors to identify the responsible species or processes and which are affecting aerosol OP. Now this is the just almost final slide, and this in the beginning I showed that from where we collected the samples. Now I am showing overall results. So this is the composition over all the sites, and you see this red one is opium, green is OPB, and black is mass concentration. See just few things carefully. You see black versus red and green here, black versus red and green here and here, and means in between. So you are seeing quite a bit, means quite significant differences. Their mass is more compared to the other bars. Here these bars are going much up compared to mass. So why is it so? It is same thing what we were discussing. So this is Shillong or Port Blair. You are getting aged aerosol masses from Indo-Gangetic plain. Aerosol atmospheric processing are increasing their OP. Arabian Sea, mineral dust was coming. Mineral dust is TTT inactive. So you have more mass, but OPB and OPM were low, and other things were in between. So from our study over urban, semi-urban, mountain and marine regions, this is the major conclusion we draw, that one thing is OP of species coming from biomass burning is much higher than whatever is coming from fossil fuel burning. Other is OP of anthropogenic aerosols are more than natural aerosol, as you can see from here. Aerosol OP is governed by the chemical composition rather than total mass concentration. Oh, I missed that. Atmospheric aging. So this is the reason. Atmospheric aging or fog processing increase the aerosol OP. That is why you are getting this kind of trend. And aerosol OP is governed by chemical composition that we have already discussed rather than total mass concentration. So what overall it says that mitigation strategies for reducing aerosol concentration alone may not work, and linking aerosol OP with health effect will be more effective. As far as, suppose if you are saying that just reduce the mass concentration of aerosol, that may not help, because fraction of redox active species present in that, if you are reducing that, that only will affect as far as health effects are concerned. So to summarize whatever I said so far, so this I think I have already said, so one can read.
Okay, thank you, Professor Neeraj. We can take few questions.
And I wish to acknowledge my supervisors, actual people who are working, I am just presenting, and my wonderful collaborators. And these are our publications from aerosol OP work. Yeah.
So I don't see any questions. So, oh, okay, Subrata.
One question, actually, in your earlier slides, you have shown one comparison of chlorine deficit with excess sulfate. So all the measurements are from cruise, right?
Yes.
Okay. So whether you have seen any seasonality, because the source of H2SO4 in ocean mostly from DMS, maybe, right?
H2SO4 sulfate.
Sulfate, it's a exchange reaction. Okay. H2SO4 with.
Okay. So season when you say, all these cruises were taken during January, February.
Okay.
Winter time. So you know that time you get the plume from Indo-Gangetic plain.
Okay. Right? Okay. So it's mostly continental origin.
Yes. Sea salts are obviously from ocean, and other things were coming from. So that is why you have to get NSS sulfate, non-sea sulfate. Yeah.
Okay, let us thank Professor Neeraj. Yeah.
Yes.
What effect, say for example, in case of Western IGP, which is dominant by the dust aerosols, and the Eastern IGP, which is more dominant by the polluted aerosols. So how do you think in your theory this will impact the overall process?
It affects almost all the things, means whatever we say, initially I was talking about the solubility of iron. We have shown that if we are collecting aerosol over Arabian Sea versus aerosol collected over Bay of Bengal, solubility is much different. Here it is 1%, 2%. Here it is going up to 40, 50% because of this kind of reactions. Same thing means I have shown that bar, that red and green versus black. You have seen Port Blair and Shillong, that how much different they are compared to whatever you were getting over Arabian Sea. So this processing is
Any data from Western IGP like
Patiala, means Western IGP is Patiala, but means during winter we have done.
Okay, thank you, Professor
Thanks.
Neeraj. So we'll move on to the next talk by Dr. Soumya Singh. She will be talking on atmospheric ammonia measurements, sources, processes, and its impact on air quality. I think we are on time, maybe 2 minutes.
Is it fine if am I audible? Perfect.
Which one?
Yes. Soumya? Yeah.
Next slide, and this slide, and this is the font.
So, hello everyone, good morning. My name is Soumya Singh and I am a research scientist at UC Berkeley. I will be taking you from air to soil to vegetation a lot, so just bear with me. And so first of all, I want to thank organizer and Vijay especially, because my talk is I'm not going to talk about the particle a lot, but I still feel like, and you will agree that, ammonia is so relevant. So yeah, thank you all the organizers and thank you University of Hyderabad. So let's start with acknowledging my group so far. So I did my PhD from JNU, and then I went to do my first postdoc in University of Toronto, where I did a lot of ammonia flux measurement and I learned a lot about ammonia exchange from atmosphere. And then I am currently with UC Berkeley, so working on PM 2.5 measurement. Okay. So usually I don't go with the outline, but because it's I figured that this is going to be quite a mixed audience, so I just thought I'll give you an idea how my talk will be going on. So I'll talk about some, first I'll give you the introduction of the ammonia hotspot, why exactly I'm talking about ammonia here. But then we understand, I'll go with from the sources to the sink. So what happens once it's in atmosphere, and then how it impacts the air quality, and then also when we look back a few years back and how we see that trend is going on. So just to I have written this for me, that also to explain that my talk will be, I'll be going from the global, I'll just show the global trend or global chemistry or whatever the deposition or emission I will be, and then I'll be also giving the Indian scenario. I try to patch that with my work, and also brought my other research group study as well. So yeah, so let's look at what is these global ammonia hotspots look like. So basically with the evolution of the satellite data, and we can see this beautiful picture when we see that ammonia, this is basically the atmospheric infrared sounder satellite, which actually measured the ammonia concentration. So I think this is a recent development. Recent, when I say, it's like around 2002 or something, the satellite came, and we can actually see that these are the major hotspots, and they identified the major hotspot globally, and IGP and India is one of them. But when you look at the trend of and they looked from 2002 to 2016, and they came up with this difference of the ammonia rate per year, how that is changing. So the warmer color you see here, it's basically showing the it's increasing over the time, and when you see the cooler colors, which is like in blue, it's showing the reduced, because of the reduced agriculture burning, they are seeing the decreasing trend. And of course we are here, we are in the warmer zone. Warmer means the increasing zone basically. So starting with the ammonia pollution. So what is this pollution means? As we all know by now that ammonia is one of the most alkaline basic nitrogenous species in atmosphere. It acts as a precursor and it reacts with the acidic part of the atmosphere, which is like acids, sulfuric acid and nitric acid, and form the PM2.5. It can actually deposit to and also create the haze in densely populated area. It can also deposit to the sensitive ecosystems. So let's get deeper into the source and sink process. So now we are talking about the sources. So ammonia agricultural activity has been the largest source, which account around 80% globally. But when I say agriculture activity, it also includes the fertilizer application and the animal farming and all. And then there are biomass burning, vehicles, industry, and natural sources as well. So once the ammonia in atmosphere, of course, anything goes in atmosphere, it will come back. So it has sinks. As sinks can be atmospheric chemistry happening in the atmosphere, reacting with the acids, and then forming the particle, and then implications on the air quality. But then it can also deposit to the surfaces like water bodies, like soil and forest, and then it has further impacts like soil acidification, agricultural productivity, eutrophication, and climate change. So now, this arrow was intentional because I'll be talking from one of my measurements we did in Ottawa. So I'll be talking about ammonia exchange with the surfaces bidirectional. So this was not by mistake. Just wanted to help. All right. So let's look at what is the atmospheric global budget, because I'm moving towards the sources of ammonia. So it's important to see how this is. When we see different source contribution. So basically, this is not a very recent paper, but ammonia is so difficult to measure because of its, it's a very sticky and volatile gas. So this has been always a challenge, whether you have a very integrated measurement, which can be like 8-hour integrated measurement, or something a fast response measurement. So this paper actually, they took the data, wet deposition data from different measurement monitoring network across North America, Europe, and China. So like NADP and then CapMon from Canada, and they took the ammonium wet deposition data, and they actually derived that to the ammonia emissions using different emission inventory. So you can see that the fertilizer and manure actually contribute a lot, and that's where so my talk will be mainly focusing on how much ammonia agricultural and food process system is actually going to contribute to ammonia, and how that is what are the other implications to that. So yeah, these are two major impacts. So let's look at the agriculture and ammonia separately. So once you have fertilizer activity is one of the major when you think about the agriculture activity. So fertilizer application is one of the major component on that, and urea is one of the dominant fertilizer when we think about fertilizer across globe. And once you apply urea, it get hydrolyzed with the water moisture inside, present in soil, or with the irrigation, and with the help of this urease enzyme, it creates ammonia and CO2. This ammonia can actually escape, but we are putting this urea because we want to give food to the plant. So it can actually, it can do its own work, go to the nitrification and the nitrate, and then plant can take that. But what happens usually, it actually immediately escapes from the soil, and that's a problem for farmers, because there is a term called nitrogen use efficiency. So basically, how much nitrogen you are putting in the soil, it's not going to the plant. So that's also reducing. And then what's happened, if this ammonia is going to the atmosphere, that also creating the PM formation and other implications. So we are basically losing, there are many implications coming from the economic cost. We are from the fertilizer application to the environment as well. All right. So there has been many, attempts, I would say. There has been many effort to really come up with how much actually ammonia is coming from these fertilizer applications. So I put together this chart from this paper, and basically they, you can see the nitrogen loss in form of ammonia after urea fertilizer application is from 30% to basically 12 to 15% in Europe, and South of Asia is one of the highest contributor. There is no surprise because it's a mainly agriculture dominated area. But why this high variability we see? Because of, there are, as I mentioned, ammonia is really challenging measurement. It's an extremely challenging molecule to measure, and also there is, because of the advancement in the instrumentation recently, we are able to actually measure ammonia in a better way nowadays. So I was doing, so as a part of my postdoc in Toronto, we had this motivation, okay, so what happens if we go to the farm with a fast response measurement, and if we really conduct a 2-year experiment in the field, and do we see that high emissions coming from urea application? So we collaborated with the AFC, Canada Food Inspection Agency, and they have like a beautiful experimental farm where they have this flux tower, and they have this sonic anemometer, and they do N2O flux. And so we had our instrument which is called quantum cascade, which is called quantum cascade laser spectroscopy, QCL. You can see the full form here, and it's basically a fast response measurement, and it measures every 10 hertz. So every millisecond you will have a ammonia data. It measures the concentration, but when we actually measure the turbulence, which is the vertical wind, we can see the covariance, and that's how we derive the eddy covariance flux. But I have put this for the simplicity, but it took 1.5 years to really clean the data. So it's not that simple. It's a complex process. But this is our experimental setup. It has the analyzer, basically the QCL, and then you need because it's a laser instrument, you need a chiller to cool that. So I will not go into the detail about the instrumentation here. And just to give the perspective how this data looks like, it's a millisecond data, so this is just the time series to show. This one is the ammonia concentration in ppb, temperature, and the wind speed. So whenever you see there is a spike in the ammonia data, and if it's co-vary with the wind speed, basically that time you understand there is a flux. But this is exactly not the process we compute the flux. There is in background we have to do a lot of computation and a lot of calculation, but this is just to show visually how that time series would look like. All right, so we got 1 year of data. I'm just presenting 1 year of the data. But as I mentioned in the first graph, that when I was describing the process, ammonia is actually, it can emit from the soil to atmosphere, but it can also deposit if they depending upon there are different parameters. So we did actually capture emission, deposition, emission, deposition. So this is basically a one full growing season data, and then on y-axis you see the flux that's in the nanogram per meter square per second. So whenever you see a flux value more than 0, then that's emission. Whenever you see value 0 less than 0, that's basically deposition. Sorry. All right. So thank you. I really need this. So to actually estimate how much ammonia is coming from the fertilizer application, we basically look at just a few weeks of the data, because once, think about the crop. You start growing the crop, after a few weeks it will just grow. So then the atmospheric exchange with the soil actually just break. Then the coupling start happening with the atmosphere and then the canopy. So we basically, that's the reason we only take the 3 to 4 weeks of the data, depending upon the canopy growth. So here you see other parameters which are being measured on the field, and this is the mixing ratio. So we also collect the soil data just to make sure that we have the measurement of the flux, but also we want to model how that actually correlate with the soil data, because it's all happening inside the soil. So what happens that there is an atmospheric concentration, but there is also a term called emission potential. Emission potential is basically the ammonium concentration in soil and then the pH. So you can compute that emission potential. And based on that, there is, the basic chemistry based on the Henry law constant and acid dissociation constant, we can actually we can actually derive that what would be the direction of the concentration going, if it's going into atmosphere or not. So based on that, we also found that, okay, our measured value were very much comparable to the model, and we saw actually very little ammonia emission from our experiment. And this was a very first successful eddy coherence measurement globally, actually covering 2-year season. And we have not, I'm still working on the paper because it's just very challenging. So yeah, hopefully in 2023, yes, we will see the paper coming up. So that was Canada. Now moving back to the India. So I also did, during my PhD, we did not measure the flux, but we I actually measured the ammonia concentration in different, rural and urban region. So rural was UP, and there is a village called Mai, that's actually my village, and then Delhi. So we actually saw there was a significant seasonal variability in the ammonia concentration. And I mean, we measured concentration, but of course we wanted to trace back what is the underlying cause. So basically you can see that there is in rural area, you can see monsoon is always washout, because of the washout effect you can see the lower concentration, but in rural area the seasonal differences are very much clear. And I mean, we have these crop season, Rabi and Kharif. So you can, I mean, I'm not able to really say that I was not tracking the fertilizer activity, but in a bulk, I can say that whenever there is temperature and that's the atmospheric condition not favoring to the mixing, and also the fertilizer activity combining with that, that's basically increasing the ammonia concentration. But that also, I mean, you can argue that PM 2.5 would be also like that. So because it's a concentration, I cannot really go back into the source identification here. But so I talked about agriculture, but there have been actually the non-agriculture sources as well. Traffic emissions have been there have been many studies reporting traffic emission. So this is actually my project. It's I have been doing this, and I love giving name to the project. It's called Analysis of Measured and Modeled Atmospheric Nitrogen, and this I have been doing with my one of my colleague from Netherlands. He is a satellite person, so it's perfect to really collaborate. So just like everybody was doing COVID the data taking from the COVID and understanding how that impacted the air quality, what I thought that, okay, this is the perfect setting to see if there is any influence we see when we see the reduction in the transportation or any, the industrial activities shutting down. Do we see that data in ammonia concentration? And we have taken this data from CPCB. There are limitations in that data set, but because this data set is available, we will be, and that's why I actually wanted to just look at the data set. So I took the criteria was I will take the 3 year of data, and that's where I got just 7 sites, and 5 sites from Delhi and 2 from the surrounding area. And these green colors is basically showing the shaded color is showing the lockdown period in 2020. Then the green is the lockdown period in 2021, and you see this is the hourly concentration basically with a moving average of 2 weeks or something. So when you see, I mean, from this data is still trying to interpret, is still analyzing this data. So we don't see really a clear difference, a clear drop when the lockdown started for ammonia. Again, I want to remind about the measurement limitation. Really? Okay. All right. So this is basically I wanted to show this work I'm doing to understand what are the other sources we have. Then there are sink, and once this is in atmosphere, it can react with other So there has been studies in Salt Lake City. Why I took this example, because this is showing exactly what kind of level we see in IGP care, IGP, And that's basically my research group in Toronto. They did this measurement to understand how this is actually ammonia is contributing to the haze formation in Salt Lake City. Again, from that data set, CPCB data set, I'm trying to see how IGP and non-IGP actually reasons are are different in the ammonia concentration. And we are trying to see that from the satellite data, which is the CRIS satellite data, cross-track infrared satellite data, and how that is comparing with our measurement, ground measurement. So there is another thing which is called deposition. Deposition could be basically, it can be dry deposition and wet deposition. So from this satellite, I just want to focus on, from this graph, I just want to focus on the ammonia part, and overall the message is here, the deposition is also increasing as we go, our demand for the food and energy is increasing, the fertilizer overuse is also increasing. I can actually, basically I just wanted to talk about the deposition, and we also observed that in Delhi, that in wet deposition in last 2 decades, this was done in my PhD, we also observed that the ammonium deposition increased like 4 times. So clearly from the global satellite data, when we see that very locally from India or US or Canada, we see that similar pattern. But you need to understand the uncertainty with these measurements, or these the graph analysis I'm showing, it's huge. So that's again showing really that what we need more measurement basically, and I want to jump into this summary part. So it's nothing very like I'm not going to talk about anything, just we found something. I just want to highlight one of the goal, or actually the key goal of my talk was I wanted to talk about ammonia, which has been a not overall discussion in Indian scenario, I would say. Like people talk about it, but we need to bring the agriculture, atmospheric and air quality people together to really solve this, or to really understand this problem, I would say. So yeah, I mean, we need total NHX measurement, not just the gas measurement or simultaneous measurement. Yeah, I think I talked about it, so I can just, thank you.
Yeah, thank you, Dr. Somia. We can have a few questions.
Hi. Nice and interesting. So how soil moisture and soil acidity will affect this ammonia exchange?
How soil moisture, so its deposition actually create the soil acidification, I would say, because when if it's getting deposited and when it's get the soil moisture, it can go into NH4 plus. So then if you think about the nitrification, that will create actually from ammonium to the nitrate nitrate formation, there will be H plus, and that actually create the soil acidification.
How it will impact that ammonia exchange? Like if it is acidic. Oh, okay.
Yeah, let's thank Dr. Somia for interesting talk. And with this, we have come to the end of this session, chemical transformation of aerosols. And I thank all the speakers for sticking to the time, and I thank organizers for giving me this opportunity. Thank you. Thank you. I think we'll break for tea.
Yeah, 1 second. Yeah, thank you so much, sir. Yeah, thank you everyone. Thank you, Dr. Pandit, for chairing the session, and I thank all the speakers. We are running late, 5 minutes. I think that's all right. Jury has given me poster presentation evaluation reports, and they told me that it was very, very extremely competitive. Rather, very is not probably appropriate word. Extremely competitive, and we had to go 2 rounds, and this is what we got. Yeah, so we have M. Deva Prasad, Arun Nair, Subrata Mukherjee, Pallavi Padwal, and Oishi Chakrabarti. All of them are here. Okay, Oishi Chakrabarti is not here. Deva Prasad? Good. So Deva Prasad, Arun Nair, and Subrata Mukherjee will get a chance to give a lightning talk. in the next session. So I request you to transfer your poster file, actual poster what you presented here, electronic copy. Okay, perfect. Then that will be displayed and you will have 5 minutes. All right? Yeah, so we'll break now for tea. I request everyone to wear your tag and remain inside the premises. You will know when you go outside. And come back in 10 minutes, if possible. If possible. Or 15 minutes.
Is it the same? Okay.
It's a very little change of only one graph I changed. I thought that not. Otherwise, this will also work.
No. One second.
Because we have given one sheet earlier, Google sheet.
सुदीप साहब क्या चल रहा है? अभी चाहिए बाद में देखेंगे देख लेंगे। let you know. Okay. So we'll display this one. This is fine.
This is fine. Actually, only one graph I changed. I thought that it's not.
Okay. This is the one displayed there.
Yes, yes.
Okay, we'll do that.
I have the same one, but little like graph one graph I changed.
Okay.
So I don't know like whether it will appear in good way or not. So that's why. No issues. No issues.
This is fine now.
This is fine. This
Okay,
is fine.
perfect. Okay. So this will be in the folder.
Okay.
Okay. Fine, fine. You can go
Okay.
for.
Thank you.
Naira Parada. Hello, Parada. Hello, hello, hello. 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 Sir, pardon. Okay.
Now you start, sir.
It is going to start.
Huh?
When will it start? Who's his first stop?
5 minutes, right?
Who's his first stop?
I don't know where it is. Program should be there. Is it here? Deliver. I will go and give my bag to Naida. Okay. He will take care of my daughter. Okay. Please be here.
So I just want to check my presentation details. Right now my topic is slide change decided.
Yes, for side change this one.
This pointer.
This one is pointer. This is pointer. That one.
This is it. That's fine.
Okay, your slide is here.
Plan B.
This one right, sir?
Yeah.
My presentation.
First one. Copy into. Thank you.
Just probably not show it, but just in case. What happens if I click?
Yes, I have taken one separate folder.
Matthew?
Yes, sir, sure.
This is browser. I'm not sure if I will show it, but I want to have it
Open. We'll keep it.
Yeah. Let's.
Yeah. Yes. Yeah. Okay. Welcome back. Our next session is aerosol cloud radiation interactions. I request Professor Sagnigde to chair the session.
Yeah, so good afternoon, everyone. So in this session, we have one keynote talk, two invited talks, followed by three lightning talks. So I'd request the speakers to keep it in the time, and without much delay, I invite Dr. Pandithurai to deliver his keynote talk.
Yeah, good morning, everybody. So first of all, I thank Professor Vijay and Dr. Rakesh Huda for invitation, and I thank all the organizers for wonderful hospitality for the last last 2 days. So with this, I'll start. So I'll be talking on the aerosol cloud precipitation interactions, which is an uncertain component of climate system. So I have to thank many of my colleagues. I have not listed all the names, but some of them are here, Subrata and Pallavi, and there are other colleagues, Leena, Anil Kumar, Abhishek Ray. So I will be presenting some of their PhD thesis work. So if you see this schematic which describes the aerosol cloud precipitation related processes, which occurs in a GCM grid box. So you will see, so there are several processes which interacts with other aerosol cloud precipitation processes and with a large range of spatial and temporal scales. So here you can see the cloud types which include low-level stratocumulus and cumulus, where the research focuses on aerosol activation, and there is a mixing and new particle production in the below cloud bases. And when it comes to high clouds like cirrus, so you will see the aerosols act as ice nuclei, and in turn contributes to the ice precipitation processes. So here the primary processes are given in blue color. So whereas the secondary processes that result from and influence aerosol cloud interactions are shown in gray color. And so you all know that in high cloud active aerosols there will be higher cloud droplet, more cloud droplets gets activated, and for a given liquid water, if there are more number of small droplets, then they cannot grow to larger size, and so for a given volume, if there are more number of smaller droplets, it increases the reflectivity of the cloud. So it's widely known as Tommy effect or cloud albedo effect. When the droplets are small, it will not collide with the falling drop, and it can bypass the falling drop. Whereas the large droplets which can collide with the falling drop, in turn the collision coefficients of efficiency will be higher. So it's also known as the cloud lifetime effect. So this way, the cloud active aerosols, which could be act as a cloud condensation nuclei or ice nuclei, and it will lead to the cloud radiation interactions and the aerosol cloud precipitation interactions. So in turn, now it can suppress or increase the local precipitation and alter the thermal radiation and latent heat profiles, and in turn it can affect the hydrological cycle and climate. So there are several processes which are listed here, and so IITM took some initiatives for better understanding on these aerosol cloud precipitation interaction processes. The one was in 2009, so it was a project which used instrumented aircraft, cloud aerosol interactions and precipitation enhancement experiment. And after that, subsequently, we also established a cloud physics laboratory in Western Ghats, and currently, so we are also establishing an atmospheric research testbed in core monsoon zone, which is central India. So wherein all the atmospheric processes are could be understood, and in turn it can better represent in models. So that's the idea. So CAIPEX, this is led by one of my colleague, Dr. Tara. So it's the major objective is to understand the aerosol cloud interactions, and also to formulate a scientific basis for rain enhancement, because in India there are several state governments, which they used to go for cloud seeding projects for rain enhancement. So the ministry wanted to take a scientific basis seeding and give recommendations to the government. So with that, this project started. We got an opportunity to better understand the cloud processes. So in this project, we used instrumented aircraft, but with Aerosol, cloud, and some of the meteorological variables, but not detailed aerosol chemistry because of the limitation of the aircraft and also due to space. Even though we tried to get some chemistry, but it's not that we could not have aerosol mass spectrometer type of online instruments. So the interesting results, what you can see here is the polluted continental clouds. So this is some vertical profiles of cloud drop size distribution. In one case, continental polluted, which is conducted in 28th May 2009. The other one is near Mangalore coast. It's considered to be a clean marine case. So what you see here is the number what you're seeing. It shows the the altitude in meters. So you'll see from 4.5 kilometer to 7.5 kilometer. So in spite of cloud, sampling the cloud drop size distribution about for 3 kilometers, so the drop size distribution did not broaden. Whereas in the clean marine environment, you can see that the droplet size distribution broadened within even 3 kilometers, right? So what it does is that when there are more cloud active aerosols or polluted environment, the droplet size distribution doesn't broaden at certain height. So it takes, it tends to grow to deeper heights for warm rain initiation to occur. So it indicates that the collision coalescence is suppressed here. So whereas here the collision coalescence is active. So that's what we could see how the aerosols can influence the cloud drop size microphysics, and in turn it can affect the precipitation. So in this case, so even though the warm rain did not get initiated, but during the later part, so the ice microphysics also plays a role because so in this region during May there is a lot of dust aerosols which could act as a potential ice nuclei. So we could see some ice hydrometeors while sampling the clouds at higher heights from 6 to 7.5 kilometers. So there are some studies from IITM giving that how the rain forms at a higher elevation when there is a more pollution. So that's a thing. That's one of the study, and this graph is not coming up. That shows some modeling simulations with different CCNs. So giving a different result, giving similar results what we have seen in the observations. So this is another paper which showed so when the warm layer depth has to increase when there are more pollution. So to improve our understanding on aerosol cloud precipitation interactions, so we have certain knowledge gaps. So we don't have full understanding on the CCN and ice nucleating particle activation processes, which is representative to our region, so that these observations can help tune the existing parameterization in models, and also what physical and chemical characteristics which control the activation of complex anthropogenic and natural aerosols prevailing over these regions to how it serves as a CCN and ice nuclei. And this is the cloud physics laboratory, which you will see in Western Ghats. So I invite you, all of you, in some occasions whenever you are visiting, you can have some collaborative proposals. So we have several facilities for all these three components: aerosols, cloud, and precipitations. So also you will see that there is a high vegetation, so which you can see there is a potential for biogenic volatile organic compounds, which we recently initiated, so which will act as a potential precursors for secondary organic aerosols. So these are some of the objectives we said that how the aerosols influence microphysics and how we can develop a better parameterization for our relevant to our region, and what is the role of biogenic volatile organic compounds on secondary organic aerosols and in turn CCN activity. So those of you who are not very familiar with the Western Ghats, you can see this color is shown in the altitude, and you have a dense vegetation, and it's a highly very heavy precipitating region. So it's not very clear that the orographic precipitation in this warming scenario also has some climatic signal that there is a decrease in orographic precipitation. So how these the anthropogenic influences are altering, that's a major question here. So with this, I will divide my talk into two parts, like CCN and ice nuclei, depending on the time availability. So these are some CCN supersaturation spectra which we observed over Western Ghats, and also this is near Hyderabad. So we had some campaign to support the aircraft observations over this region. So we have CCN spectra for different regions now. In addition to these, on campaign-based Varanasi and other places. So this is one such result. We could see that how the aerosol and CCN are varying in different season diurnally, and you could see the different diurnal features in different seasons depending on the different sources and the other processes. So what you primarily see in monsoon, you will see a primary peak in the morning, whereas in the pre-monsoon you have the secondary peak is the evening peak is dominant. So the question is that in spite of heavy precipitation, even during these break situations, we have higher aerosols and higher CCN. So we were trying to understand what could be the possible contribution of biogenic VOC emissions from these regions to these organic aerosols. So we tried to look at the chemistry of these aerosols, and this shows for several days. You can see a systematic diurnal variation of high organics during the daytime from the morning to. So the kind of scenario we could see. Which we try to link with aerosol and CCN variability. So this is one day where we could see how the diurnal variation of CCN, and so compared with the chemical composition of aerosols, you can see this. So it closely resembles the organic aerosol variation. Also, we could also see some such a new particle formation events over this place. So using all these, so we try to see the closure between aerosol and CCN, and what is the role of organic aerosols. And so this shows, this graph shows this is the aerosol concentration, and these other curves are CCN concentration at different supersaturations. So you can see during the late night and early hours, the activation fraction is very close to 70 to 80%, whereas so during the daytime you have the activation fraction reduces considerably due to the complex chemical composition of aerosols. So we try to see, in the absence of the hygroscopicity measurements, we try to see using the ACSM chemical composition, we try to see whether the estimated or modeled cloud condensation nuclei, how better it matches with the measured CCN by having different scenarios of inorganics and combine inorganics and organics. And when the better correlation is seen when you include the inorganics and the oxygenated organic aerosols. So that is in the absence of hygroscopicity. Later, we try to augment the hygroscopicity measurements at our lab, and so this is the HDMA setup. So wherein so you have two DMAs. One you see the dry particle radius and send it to another humidified DMA and humidification chamber, and see the growth factor of aerosols. And from the growth factor, if you estimate the hygroscopicity, which is commonly called as kappa, and you have for different seasons, so March, April, May, and the monsoon and post-monsoon and winter. for different sizes of the particles. So this is a PDF, and we classified these data sets into 3 classes. One is less hygroscopic, below 0.1, and the other one is hygroscopic population between 0.1 and 0.2. The third class is more hygroscopic population. The shaded region is in the hygroscopic population, and you can see different type of size dependence, what you see in different seasons. So when you take a seasonal average hygroscopicity, what you see is different behavior in the Eichen mode size range, and so there is an increase in kappa from in the accumulation mode range particles, range sizes. So we try to see what could be the possible reasons. So what you see is in pre-monsoon, so the more hygroscopic population tends to get reduced. And the above 100 nanometer, you will see the more hygroscopic population increases. So this is one of the reasons for such a behavior, that so there is the reverse trend in the size dependent hygroscopicity. So in monsoon, you can see there is a flat variability, and we try to look at the PDF of diurnal variation of hygroscopicity, and the black line shows the average hygroscopicity and for different sizes. So we try to see with the chemical composition. So it clearly shows that during the daytime, in the morning hours, there is an increase in organics, which reduces the hygroscopicity, whereas so whenever you see an increase in inorganics, which leads to higher hygroscopicity, and these are some average so values what we use for. And so if you look at the chemical composition in pre-monsoon, so you have higher ammonia and higher ammonia and chlorides in pre-monsoon, which could be one of the possible reasons for increase in kappa values in pre-monsoon as compared to winter season. So we try to see the closure study between kappa derived from growth factor from HTDMA and the derived from chemical composition, and this chemical composition is derived from AMS. So one thing what you can see is that the AMS only can measure non-refractive species, and also using the ZSR rule for estimating the hygroscopicity. So you need to assume the type of aerosol mixing. Also, the transmission efficiency of AMS is also lower at lower diameter. So during measurement, a lot of particles could be missed. So if you try to use the chemically derived K in models, could add error in cesium activation processes, and which will in turn affect the cloud lifetime and closure. So we also try to see, even within chemistry, try to see the different mixing scenarios and see which one is closer to the growth factor derived kappa. So this paper so recently come in Science of Total Environment, and we also try to see whether we can parameterize this hygroscopic growth factor. So for different seasons, we try to see what could be the coefficients. So in the absence of such complex growth factor measurements, so one can use in this region, this kind of chemical composition is there. One can use this parameter, so parameterization to estimate the growth factor for any dry diameter. Now, also we also implemented the volatile organic compound measurements. So which currently Subrata is working on for his PhD thesis. So he looks at the variations in isoprene, monoterpene, and benzene toluene, and so we could see that this isoprene was highest among all the VOCs, so about a factor of 5 during summer. So this could be due to the high temperature, which results in a higher isoprene emission. So when you look at group the data with the temperature, So you can clearly see that there is a good amount of emissions when the temperatures are increased. So here I try to also see that how there is evidence from the VOCs, and how do we see that SOA in the AMS measurements. So you can see that there is a time lag between the VOC measurements, isoprene, which is shown in green color, and what you see on the right hand side is from the AMS. So he further, he plans to utilize all these data sets to assess the SOA formation using a box model. So to estimate secondary organic aerosols. So this could be, so the estimated SOA can be further compared with the oxygenated organic aerosols, which we can estimate from the AMS data. So how I'm doing time? So okay. So now I'll shift slightly from the CCN to the ice nuclei. So aerosol also facilitate the nucleation of cloud droplets and ice crystals in the Earth's atmosphere. So what you can see is that there are more ice nuclei, there is more ice and precipitation, so which is leads to shorter life and in the low level. And if very few ice nuclei, then mid-level clouds persist as liquid, so which can lead to net cooling effect. So here we try to measure the ice nuclei and try to parameterize from based on observations. As you all know, as compared to CCN, the ice nuclei are very few in number. So you can say 1 in million of aerosol particles. So here we used a continuous flow diffusion chamber for online measurements of ice nucleating particle. So very few studies were carried out. We conducted an aircraft collecting samples, and there are other previous studies also, offline samples, and do analysis in the ice chamber. And we don't have continuous measurements, and so if we have continuous measurements which could use be used to develop a better parameterization to improve our climate prediction. And this is the spectrometer for ice nuclei we use, and it's a CFDC type chamber, and this is a semi-automatic instrument, and so there's a lot of effort is required to conduct one experiment, like almost 8 hours a day one has to work on to collect data. So I think I'll skip these technical specifications. So basically the ice nuclei, so we try to look at different seasons, mainly in these mixed phase temperatures, like below minus 25 degrees onwards up to minus 34 degrees Celsius. But now we are also parallelly collecting some samples on assay and try to go even below this temperature to get the ice nuclei concentrations. And as you know that there are the existing ice nucleation parameterizations some are supersaturation dependent, some are temperature dependent, and there are some temperature within aerosol dependent, aerosol concentration dependent. So we also try to put our measurements into the temperature and the aerosol dependent method, and we try to derive similar to the Paul DeMott parameterization. But so this is one of the paper which came out that how even the DeMott equation, which he uses similar parameterization, but it doesn't fit to our region. So we used our observations and tuned it to match better with the observed INP concentrations. So also we tried to test this in the model, and I think I'll skip this. And so it is tested in WARF model to see how these different parameterizations fare well with this, and so which shows that we also try to compare with radar reflectivity. So what we see by implementing our parameterization in the model and see how it compares well with the observed reflectivities. There is a reasonable agreement, but still there are a lot of biases which further need to be tested. So we also try to see how well it simulates the raindrop number concentration or raindrop size, and we see that the IITM the spin developed parameterization matches closely with the observations. I think so. With this, I think I'll summarize in the interest of time. And so to summarize, that the aerosol particles are necessary ingredient for cloud droplet formation and ice nucleation process. So how they can modify the cloud microphysics in sometimes in subtle ways to generate feedbacks that may amplify or dampen their influences. So aerosol dependent ice nuclei parameterization for our region is developed and tested in models. So cysteine activation process studies are being made using size resolved chemistry and hygroscopicity observations. So these observations are essential for process studies and also to develop parameterization representative to different climate regions. So with this, I thank you all. And so all these measurements over orographic regions generally represent the orographic convection cloud processes. So we also setting up a atmospheric research testbed site in central India, which is a core monsoon zone. So if we can improve the prediction in core monsoon zone. So core monsoon zone rainfall is highly correlated with all India rainfall. If we can represent the processes in the core monsoon zone, so which will be more realistic representative for the region. So whereas the Western Ghats cannot represent the entire India. So that's the idea that we are also coming up with developing the testbed facility. So I welcome all of you to join in this effort. So maybe in future we will have proposals from MOES. You can also submit proposals, and it should be like our dream is to have like a DOE arm type of site, which is there in Southern Great Plains in Oklahoma. So similar to that. So this is a plan of Ministry of Earth Sciences, and we are trying to implement this project. So we already set up a suite of instruments, but still need to add many more. With this, I think I'll close. Thank you.
Yeah, thank you, Dr. Pandit, right on time. So, questions? Yeah, please.
Yeah, it's nice lecture about aerosol cloud interaction. Just I want to know, how does aerosol layer like vertical distribution of aerosols affect the aerosol direct radiative forcing?
Okay. Yeah. So the direct radiative forcing is like how it influences the radiation budget at the surface and at the top of the atmosphere, and the vertical profiles will give the alter the heating rates in the atmosphere. So the heating rates are changed, then it can affect the stability of the atmosphere. So if there is a highly absorbing type of aerosols, the atmospheric forcing could be on the higher side, so which will lead to the more absorption and more heating rates. Yeah. The vertical profiles are important.
Okay, thanks for the very good talk, and I was especially happy to see the ice nucleation measurement being conducted at your station, and it's impressive that you used the spin as the first time in India. Maybe more of a comment than a question, but these kind of ion measurements, they are really crucial because they basically dictate. You cannot have rain from a cloud without having ice nuclei in that, basically, because that's the only process how you grow the droplet to a large enough size. And it means that these kind of ion measurements are very crucial and understand what the ion is made of and what are their distribution. And I fully can recommend that these kind of measurements are conducted in India in different kind of environments. It doesn't have to necessarily be the spin.
Yeah.
Because what can be done is normal offline filter collection, and those filters are then analyzed for the ion activity. There are quite simple methods for doing that, and we'd be very happy to give pointers and facilitate this work.
Okay, yeah, thank you. I think so. Spin advantage is only the continuous online measurements, but there are problems with the spin that we cannot go to high temperatures, below minus 25 as of now. We also have parallelly started collecting samples in central India and to analyze it in offline. Yeah, so.
No, I think in the interest of time. Okay.
So, the increased CCN, they reduce the cloud effective radius. That is the normal Tommy effect that you have observed. Have you observed something like anti-Tommy effect in which for some of the particles, the increased CCN is actually increasing the cloud?
Yeah, so that is also there. I think in some cases we also noted there is a paper also by anti-Tommy effect reporting. Even from satellite data, many people are also seeing that there is an increase in aerosol load and increase in effective radius. I think it mainly depends on how we will see the liquid water. Yeah. So even our some aircraft observations were suggesting that there are anti-Tommy effect in some conditions. But it's not very. Still, there are uncertainty in that.
Okay. Thank you, Dr. Pandit, once again.
Thank you.
So our next speaker is Professor Chandan Sarangi.
Hello. I would say I'm waiting for 2 seconds to say good afternoon to all. And thank you very much, Dr. Kanavade and Dr. Huda, for inviting me at this STM platform. I have been hearing the entire discussion since yesterday, and it's quite stimulating. And you would see I have twisted my topic also, because I want it to be more relevant about what we are discussing. At the same time, I thank Dr. Pandithurai to set up the platform and the questions from audience also. I see a question about vertical distribution. I will talk about it. I see a question about CCN anti-Tommy and non-CCN microphysical effect. I will talk about it. So what I want to say is, since yesterday we are talking about measurements at local scale, we are trying to, or we are underlining that there is quite uncertainty or deficiency of our mechanistic understanding of how these nano or questions relevant to nano symposium, how they are changing. I want to bring in another complexity. I think since yesterday we are discussing about complexities only. Every speaker is adding a little bit more complexity into the discussion. I'm saying regional emissions, right? You're measuring at one site. How does the regional emissions play or bring into or come into picture when we are discussing this? What I will do, I will show 2 case studies from my recent studies. One where regional emissions are actually constraining the air quality pattern understanding. And it's the popular case of Delhi. And I will directly go into it without much introduction because everyone knows about it. Second, I have a relevant question. Does, since last 10 to 15 years, we are continuously seeing observational evidence that aerosol cloud climate is a thing in India. But does this aerosol, and we also know that aerosol emissions are increasing. So do we see a trend in cloud cover based on this increase in emission? These are the 2 case studies I will discuss, and towards the end I will bring back the questions to our relevant discussions that we are having. So first about the trends. We all know now that India has or specifically Northwest India has a new season. We call it crop residue burning season. And why it's so distinct? Because people are now actually booking or planning their vacations out of Delhi during November to avoid the hazy environment out of it. We know the very basic cause or the basic discussion that goes on is all about the crop residue burning. We have a source region here, and the meteorology favors advection of aerosols or smoke plumes into Delhi microenvironment, and we believe that Delhi high extreme haze conditions episodes that are somehow linked to it. We see model simulations, quite regional model simulations, which go from 20% to even some cases where 70% of the contribution is being identified to it. But at the same time, recent papers, well, in which Dr. Kanavade is also the first author, we talk about that meteorology is not insignificant. In fact, meteorology can actually determine if it will be a extreme hazy day in Delhi or not. What I want to highlight is last 5 years we have CPCP measurements now, and if I divide the measurements based on the fire count, right? I get satellite fire count. All these points are CPCP measurement of 4 years, 3 years, 2018 to 2020. I divide the days into high fire days and low fire days, and I put two composites out of it. And what you see is here the difference. It's very evident what we all believe. Delhi is getting the burnt, right? The maximum increase in PM 2.5 is happening over Delhi, while the source region is this, correct? This is 3 years of data. Maybe at the first stage I am surprised seeing this spatial pattern. I know Delhi is highly getting polluted by haze, but why there is less increment of PM 2.5 near the source region? That is one question which came to me in the initial part. But then I thought it might be 3 years of data. Let's do a little more due diligence. We went on with, this is machine learning based PM 2.5 estimations of 1 kilometer MAEC data. And if you use the same to again characterize the same days that the same procedure going for low fire days and high fire days, and this is the difference. You still see the same pattern, right? Over the source region it is less, and over the Delhi region the PM 2.5 values are high. So based on this is the general question I have. So if you have the smoke burning happening, it's like, just imagine like a chimney plume, it might be advecting based on meteorology. However, as we know, as it advects, it gets diluted. So why it is that, if we are saying that it's just dispersion or advection, Delhi is getting this spatial pattern, this proportional increase in Delhi, right? In some papers, people have explained that it might be a chimney effect. Whatever we are releasing, it goes up and then subsides near the Delhi region. But why Delhi region? Why not just before that? Why after that? While 20 years of data clearly shows that distinct air shade over Delhi region, right? And what I will show in next 2 slides based on my analysis is that there is actually a plume behavior movement which is happening, and there is the elevated smoke layer which is closely observed in the distinct Delhi air shade during these high days, and which can affect the temperature and local lapse rate so strongly that Delhi, or this could be a strong contributor to the spatial pattern that I am seeing. Slightly touching upon the question asked in the previous lecture about the vertical distribution. So this is, another thing, all the 2 plots I showed before, these are daily measurements. So I wanted to see if it is more in daytime or nighttime, the increase that we are seeing over Delhi. So I have taken PM 2.5 measurements which are like 30 stations over Delhi, and I have plotted I have first divided into two composites, smoky days and background days, and this is the diurnal plot. And this is the difference, right? Interestingly, you will see that the increase is maximum during noon time. You see, during basic diurnality understanding, the concentrations or dilution should be maximum in daytime, and we are seeing the diurnal pattern correct. But the difference shows that it is quite high during mid-noon time, and then it persists as the boundary layer also subsides. So this is the first point which indicates there is a role of local atmospheric structure or lapse rate and aerosol temperature interaction. Somehow the smoke plumes are affecting it. I then used, I think, 15 years of Calypso data to find out the specific days when the high smoke plumes are transporting from the region, source region towards Delhi. So one is smoky days, blue is background, and the difference. And this is at source region, but let's say Punjab, Haryana region, and this is downwind means NCR or Delhi microclimate region. What I am clearly seeing is a elevated layer, right? This is average of many profiles which are collected within those 15 years. This is the difference, or this is the enhancement of aerosol as a vertical column when smoky days are prevalent over that region, and this is the same enhancement during the same smoky days but at a higher altitude, right? And the last slide that you are seeing here, this is from radiosonde data. So we have taken radiosonde data, we have calculated the VPT based mixing layer understanding. Again, the difference clearly shows that there is a decrease in mixing layer height. Like in the background, it used to be somewhere around 1 kilometer, and during the smoky days, it comes down to around 0.5 kilometer. And this is again like average of many profiles. This is the row. I think the N count for radiosonde is around 100 or 112. Based on this, and this started to. This is also a plot from radiosonde, the same thing, mixing PM 2.5 and mixing height. Mixing height calculated from radiosonde. We clearly see as the mixing height decreases, the PM 2.5 values increase, right? To confirm this, I have also done a WorkCam simulation of a very distinct event where actually the elevated layers, Delhi is seeing elevated layers of these plumes, and I will not go into detail, but clearly you just differentiate these red and black line. So red is, green and black line. So without radiation and biomass burning emissions, which means that we are taking away any interaction with the temperature of atmospheric structure, and then the default. And it's so surprising that the values could be around 50% different. And this is a specific case when the plume is actually located 500 meter above Delhi. It's just passing by Delhi, and this could be an effect. So this is the first case study I was talking about. Regional emissions, right? We are measuring over Delhi a lot of things, but are we considering the effect of that regional emissions or the regional thing that is coming into picture? And that regional emission is very well coupled with the atmospheric structure there. Yesterday, Dr. Lubna was mentioning about her chamber experiments where temperature is a constraint, right? If you change temperature, your questions, the growth rate, the NPF, everything changes. So in that context, you see a slight or without regional constraint, you can be missing a lot in Indian context, right? Now, I will go to the second case study I want to emphasize. As I mentioned, like we are seeing regional emissions are changing, increasing over India last 20 years. We also know that aerosol cloud climate is evidently seen in last 10 years of studies. The KIPEX experiment was the first to see the instantaneous effects. Satellite data confirms. Dr. Nair is here, who has also been working on it since long, and we know that there is a aerosol climate. Dr. Dey has also worked on this extensively. But my question is, are we not seeing the cloud cover trends? Right? It is changing. So if it is so certain, are we trying to see the cloud cover trend? And this talk will be towards the end. I will try to convince you that we are seeing. That's the thing. This is a study again we did with Dr. Kanavade in 2019. And what we tried to show here is that the increase in high AOD or high pollution days in last 2 decades is highest over southern India, right? Peninsular India or eastern India. And we have just divided the days into percentile of AOD, and this is the number of days when in a season of February, March, April, May, the number of days where 66 percentile of AOD is crossed, right, criteria. And we clearly see there is a stiff increase. Followed by this, I also worked on another paper where we used high resolution Miser and MAYAC data, and again the same picture is coming out. These are trends or changes. This eastern region, or we can call central India eastern region, there is a lot of, the enhancement is very high, not absolute values, because absolute values obviously IGP is higher, but the net change is higher. And we know by theoretical understanding that change from clean to slight pollution can be more sensitive in terms of climate compared to mid pollution to high pollution. The sensitivity is more when we change the clean environment to polluted environment. Now this and then we also want to know why it's increasing, and this is a old paper where tracer experiments were done using regional model by Kumar et al. And we can clearly see that it's a regional thing, and if you have tracers in this eastern box, most of the pollution over this eastern coast is being governed by it, right? So it's somehow related to the eastern IGP, most of the contribution. So the enhancement could be due to enhancement of regional emissions in eastern IGP. And is it, first of all, like the first thing, is it showing a relation with temperature trends? So we involved in a paper where we tried to took the same box. What we calculated is change in temperature per unit AOD, and for 20 years. And this is a paper from JNU with Amit Mishra, Dr. Amit Mishra, and Dr. Singh is also co-author sitting here in this paper. And what we clearly see is that the cooling trend is available, and in short, this region can be thought that aerosol is trying to affect the temperature trends very clearly. Then does it also affect the cloud trends? This is also the outflow region, and what we have done is the first decade versus the second decade. This is AOD. We have plotted the composite. You see that the values are strictly changing. This is a Calypso analysis of the same composite. You see in the recent time, the enhancement is at an altitude of 1 to 3 kilometers. It's not at surface that much, like not within the boundary layer, but above boundary layer. And what you are seeing here is the values of AOD summed over only this layer for last, I think 7 to 19, and you can see increasing trend in this, that the AOD over that region at a certain elevated height is increasing. And we know, and if we go and see the cloud cover over that region, the same box, this is level 2 data of MODIS, and again composites into first decade and second decade. This is the difference, and this is the trend. We clearly see that low cloud trends have been clearly increasing over this region, and the difference is very, and this is about occurrence, cloud occurrence, and the difference is very clear. We used temperature profiles from ARIES, and we found that a very clear increase of temperature. This is the difference between those two composites, while the difference of RS shows moisture increase at a lower surface. And so what I'm trying to say here, the elevated layer of aerosol, the increase in trend, can have a trend in temperature, atmospheric temperature, can increase the stability, can actually enhance the moisture in the boundary layer and affect the marine clouds. And we are seeing a trend in it, right? This trend is strong enough to also be visualized in SST trends. So generally, everywhere it's increasing because of our global climate change. But over this box, it is actually decreasing. I'm also trying to simulate this, however, capturing those trends and also the shallow clouds is a challenge. But I want to believe that this could be a location where constant emission enhancement is being seen. This is a pre-monsoonal time where, as Dr. Pandithorai told, our kappa is too high, hygroscopicity. Measurement shows around 0.2, 0.3. So this can be linked with aerosols and could be a potential region where you see trend associations with it. Just to summarize, we have papers coming out. In the entire discussion, we are seeing that temperature and the composition of VOCs, amines, sulfuric, these are the things which have the drivers for aerosol NPF as well as growth, right? These are actually, you see, people are putting papers where temperature, monsoon-driven organics are being accounted or driver for new particle formation. In this context, the two examples we talked about, and if you link it back to your measurements, you will see that there could be a strong connection or driver contributions in it. And to address that, we need to have regional model simulations. So at this platform, I would also like to encourage, I'm in trying to do some regional simulation at this scale, but I also feel that we should acknowledge the importance of regional models here, and by the next time we should have more. I believe people can have more into this. Thank you.
Very nice talk. I have a few things. See, this burning, I think it's not new. Since 40, 50 years, burning is happening. But why only the recent decade it has been highlighted? If the downward is means what you are telling is right, it should be like 40 to 50 years back also it should be happening. I think that anthropogenic activity and the boundary layer dynamics, it is what it has to explain. But not only the burning activity. That is first thing. Second thing is you mentioned that trend. You see, the trend is not linear, and that depends upon starting point and ending point. If it is a linear trend, if you put it, I suggest to have the multi-regression analysis, because sometimes it's decreasing, increasing, decreasing. You should remove the background oscillations, natural oscillations, before getting one, before putting any trend in that one.
Yes, I agree. Thank you. I also totally believe that the condition has exaggerated because of wind stagnation also in the burning scale. Like every 10 years, our wind is getting calmer over that region. Future 30 years, it will be even more calmer. So the meteorology is a key player, and if we change the meteorology in our models, everything changes. If you just tweak it a little bit. So emissions are there, but the transport and the mechanism of transport, these understandings are very essential for the mitigation, definitely. And yes, obviously observations are showing a net relation, but the exact answer will come out of more mechanistic studies only. Without that, we can.
First of all, let me correct it. This phenomena is not 40, 50 year old. It's rather last 15, 20 years that this problem has come up. And why this problem has come up? Because of the government policies that they have restricted the use of groundwater and shifted the date in such a manner that now this the period of wheat to rice to wheat shifting is only 1 month. So the people have to prepare for the land, and there is no other option but to burn it and all that. Added to that, because the sowing season has shifted, and of course the meteorology is there, which is playing a role. So these two have made it complex. So this is a recent phenomena, 2025. But my question is that because you are looking at the changes, with respect to say only the temperature, so and boundary layer, of course. So have you included wind speed and to see that if the ventilation coefficient has a bigger role to play in that, rather than just the boundary layer? That's number one. And the other is that is there some kind of wind shear being generated because of that your temperature change that you have seen?
No, definitely I have looked at it. First thing is we have handpicked the events, high fire and low fire, and we had radio sounds where wind velocities are there. They are not very distinct over that time, and it's stagnant. Like it's not very high. The wind speed is also not high, and also the difference of wind speed is not that much significant. Second, ventilation coefficient itself has the PBL height merged inherent into that formula. So yes, the net in a nutshell, ventilation coefficient is decreasing because our mixing height is decreasing, so ventilation coefficient is decreasing. And wind shear, obviously, I have not seen, because this is just what we are talking is 1.5 kilometer, and what is changing is 500 meters. So without this high resolution LIDAR observation, we might not see it. And having more LIDAR observations like over that region might also confirm and give us more events to compare and understand.
About this interesting discussion and move ahead. Thank you again, Dr. Sharan.
Thank you.
So next speaker is Dr. Andrew.
Okay, so thank you. I'd like to comment earlier that each presentation is making our life more complicated, or our seminar more complicated, and maybe I will try to simplify then a bit. So I will show something that we are doing at Pallastuntuри in Finland, and for us the process studies basically were made years ago. And I remember when I was a PhD student, and there was always some old professor who said that, but we did this 20 years ago. And now I noticed that I'm one of those, which is not a good thing, because we need to keep up with the development. But yes, so not only my study, of course, there are plenty of collaborators and people in our unit, in our group, who are making these measurements. And let's sit back and relax and see what we have there. First, I'd like to introduce the Global Atmosphere Watch concept, which is from WMO. Those who don't know, basically there are global stations around the world who are mandated to monitor the state of our atmosphere. So to say that, how is our planet's atmosphere doing? Is everything going well, or is something going the way it should not go? And our Pallastunturi station is one of those global atmospheric watch stations, and it's one of only the 4 stations that are above the Arctic Circle. And we started measurements in 95 and aerosol measurements in 96. And nowadays you cannot discuss global and European measurements without mentioning 2 research infrastructures, which is the ICOS, that is for greenhouse gases, and ACTRIS, which is for aerosols and trace gases. And really the idea behind these infrastructures is that we do quality assured measurements and in the same manner at all the stations where we are. This is a wintertime picture from Pallastunturi. You can see that there is basically nothing around here, only snow. It's an ideal background location inside a national park, which is quite large, and in such it represents a larger subarctic area. And what is important here to understand that we have a unique opportunity to also study aerosol cloud interactions, because the station, which is on a hill about 560 meters above the sea level, is occasionally inside low-level clouds. These kind of stratocumulus clouds, and I will show a bit later how they look like. About the history of in situ measurements that we have done at Pallas, and also for aerosols and clouds. So, like I said, in '96 we started. That was the basic aerosol number concentration that we measured then. And then also at the same time we were measuring the visibility with basically a Vaisala present weather sensor. In 2000 we added aerosol number size distribution measurements and a nephelometer. So now already 23 years of data series is available there. And then in 2002 we actually took into use this fact that we are inside low-level clouds, and we made a new station inlet so that we can study the clouds. Previously we had a PM cutoff, but with this inlet we were measuring, collecting the total aerosol and then gently evaporating the water so that we could also collect the cloud droplets. Soon after we started biannual campaigns of cloud droplet size distribution and other cloud properties. And 2005 added black carbon measurements. And then of course plenty of stuff happened in between here, but I'm just adding some of the most important additions. And now in 2022 these sort of campaign-based measurements of the cloud droplet size distribution were made continuous. To have an idea what kind of aerosol we have there at the site, here you can see long-term particle number concentration evolution. First, in a linear scale, you can see that the maximum concentrations are around some thousands, maybe 10,000 maximum. But what's important to understand in Pallas is that if you look at that from a log scale, then you actually have these, let's see, maybe I'll point this one. You actually see that there are plenty of low concentrations. What happens here at Pallas is that we have the low concentrations in the winter time, because really we don't have any local sources. And then in the summertime what we have is biogenic organic compounds. So that's mostly what is doing that. It's nothing to do with anthropogenic stuff. It's natural aerosol that is increasing the particle number concentration. So secondary aerosol formation, basically. And like I said, that we've sort of done most of our process studies, and now where the focus at the moment really is to take these long-term time series data into use. And this is to support IPCC assessment as an example. And this is just provides now an overview of the particle number concentration in different sites around the world, where Pallas, you can see, is, okay, now it's a patch, but I'll show here. It's one of the lowest stations. But what you can see here is there's this large variability in the Pallas data, which is the natural variability in aerosol concentration. And at polar sites, the yearly median concentrations are in the order of some hundreds of particles per cubic centimeter. So you can understand that it's pretty low. Of course, IPCC is interested in optical properties. You remember we have long-term optical properties of both scattering and absorption. If you look at the scattering, again, Pallas is very low compared to the other stations. And this is now a so-called base year 2017 that has been picked for the latest IPCC evaluation work from these kind of network stations. For absorption, I'm actually sorry, that was the absorption, and this is the scattering. For the scattering, Pallas is not there for the year 2017, and the reason is that even for the long-term studies that you do, sometimes you have break in the instruments and break in the date. And when IPCC report assessment studies are collected, they are very, very rigorous in what kind of data they accept. So Pallas unfortunately did not make that comparison, but in another study we compared against some Arctic stations that you can see here for the scattering, and Pallas is around the same level concentration as Barrow. If we take Barrow over here, here would be Barrow, so roughly again at the same levels. The long-term trends in aerosol optical properties, at many stations around the world they have been decreasing because of the decreasing emissions. At Pallas we don't really see from our data series any trend. This is no significant trend, but for scattering we actually see a slight increase for the long term. And it's the same as in Svalbard. And basically this has to do with air masses distribution being different with the evolution of time. But most of the stations around the world, they show decreasing trend also for the scattering. Which makes, if we turn it into single scattering albedo, we can see that at Pallas we have a slightly increasing single scattering albedo, so sort of a brightening the aerosol at the station. Okay, now I'll get into the cloud business a little bit more, and I will tell about these measurements that we do. So what most of us well know here is that when you have a cesium particle with a typical size of between 50 to 400 nanometers, then you have a situation where you have supersaturation, you get condensation, and a cloud droplet forms that is between 5 and 50 micrometers in size. And that's exactly now what we have basically utilized in our the size difference in our approach, how we want to study this. So basically we build, like I said, we build an inlet that takes in all the particles, including the cloud droplets, evaporates them slightly, so we can see what was the so-called total aerosol. And in this graph, total aerosol size distribution would be something like this. And then we take another inlet where we have outside ambient air, we have let's say PM 2.5 cutoff. So we cut here, which means that we don't collect these guys at all. And that would be your size distribution then looking something like this. So in principle, from that you miss all the activated particles, and now if you subtract interstitial from the total aerosol size distribution, you get a size distribution of the activated particles. So basically these were your CCN, right? What you can also do is you can, for those particles, you can deduct a so-called T50 diameter, so the diameter at which 50% of the particles were activated. In this case, it would be around 50 nanometers. So you can see the Aitken mode particles get activated at Pallas. What we then did was that we took this information and we calculated from this T50 diameter basically the CCN concentrations for a certain period of time. I won't go into details because we want to make a little bit more studies out of that. But what we get is CCN concentration, long-term data set, not in some artificial supersaturation, but actually in the supersaturation of the actual clouds. It also equals that this is basically the cloud droplet number size distributions, number concentrations, sorry. And you can see that they go from one particle, roughly one particle per cubic centimeter, up to about 1,000 particles, 1,000 cloud droplets per cubic centimeter. And you can see a trend. There's been a trend of about a little bit less than 20% decrease during this time. To get an idea what the clouds look like, this is a typical situation. So this is an image taken from a drone, and our station where we make the measurements is here. So you can really see that we are not measuring something local orographic cloud, but we are measuring this kind of a large scale, mesosynoptic scale stratocumulus clouds. Of course, we want to look into more detail. So, like I said, that we made these biannual campaigns. Since 2004 we started, and we have made 9 campaigns in total. We always hit our campaign times in the autumn, because that's when you have the maximum clouds present. About 30 to 40% of the time you are in cloud. And we measure all of these parameters that you can imagine a little bit more. And we always have international collaborators with us who are interested in these kind of studies, and they come with their own research plan, and they measure, for example, they can measure with aerosol lidars or cloud radars, or make ice nuclei measurement with spin, and so on. And by the way, this guy over here now is this continuous cloud droplet measurement sensor nowadays that we are using. It's from German Pallas company. Also balloon measurements with tethered balloon, but nothing as fancy as ISRO. And now, based on those campaigns, just maybe one highlight result that we have. So this is the size distribution of the cloud droplets in different kind of air masses. And I highlight 2 of them. I highlight the Arctic air mass, and I highlight the southern air mass, so continental air mass. So when the Arctic air mass you have here is very clean, about 20 cloud droplets per cubic centimeter, and you have the grown to a little bit larger sizes, more than 10 micrometers easily, being the effective diameter of the droplets. But when you have the continental air masses, when you have a little bit more stuff coming in from the lower latitudes, then you also have smaller sized particles, smaller sized cloud droplets, less than 10 micrometers in size. And now I still turn into one corner, because if you remember, I showed that we have this visibility sensor since the very early stages of what we had in Pallas. So the question is, of course, that there has been climate change, and there has been climate change in Arctic areas, happens 4 times faster than anywhere else. So do we see any effect at Pallas? And the answer is yes. So this visibility sensor reading can be basically converted into extinction coefficient measurements, and then what we've done is we've taken a conventional cut of saying that less than 1,000 meters in visibility means that you are in cloud, and then we are seeing the cloud properties that has the extinction coefficient changed, and there you can see a slight slope. Maybe it's not so visible there, but looking at the numbers, there's a statistically significant decrease of 16% in cloud extinction. My last slide, basically. What about nano? Because this was also one of the questions that we wanted to see the new particle formation. And this is now just one case example that we have. What you have in this picture is a timeline. So basically there is 3 days of data is here on the x-axis, and then what you have is interstitial size distribution. Then you have cloud droplet size distribution. Then you have rain droplet size distribution. Let's start with this middle guy, because you see new particle formation quite clearly, right? And you can see that there is basically no rain and then coming. But then what happens is that we have a cloud coming in, but actually we should say that it's not the cloud maybe coming in, but we have the particles disappearing here. You can see that there is a bit of a hole. If you look at the previous day's data from here, you can see the hole even more prominent. And these are the activated particles, right? They are in the interstitial DMBS data, size distribution data. So these are the guys that made into the cloud droplets, but not the size distribution measurement. And they have grown into these cloud droplets that you see here. So in the micrometer size range. And actually what you then even see is the rain droplets coming in. So you can see the cloud droplets raining down, which means that in this one figure, as an example, you see the full life cycle of an aerosol particle starting from the gas phase condensation and coming down as rain. My conclusions, I won't go through them because I probably said it already, but the take-home message is that if we see in an area, Palastunturi, where the sort of changes in aerosols have been modest in the last 20 years, and if we take this sort of same process level phenomena to India, you can understand that these kind of issues are prominent here and they are happening in the atmosphere. Thank you.
Yeah, thank you, Dr. Antti. Any question? Yes, please.
Thank you for the nice talk. I have a question related to the Global Atmospheric Watch site. So, is that how this is being decided? Like the data is being taken into IPCC report, so that's super important. How that? Can you comment on that?
How do you mean? What is your question related to?
So my question is, do you have any idea how this? So, like out of those 28 sites, how that is being? Is there any criteria for that Global Atmospheric Watch site? Because there.
Yes, for the Global Atmospheric Watch site, there are criteria given by the WMO that if you fulfill and you submit your application, you may become a Global Atmospheric Watch station. Then if we come into these, let's see, these kind of studies,
yeah.
Then, well, this was a coordinated effort from Europe, basically, that we did, and it includes more than just the Global Atmospheric Watch station.
Okay.
They gathered data from anywhere they could get hands on. So also, for example, there are some stations in India that are belonging here. I cannot now found it, but at least the measurements from Mukteswar were part of, maybe not this one, because 2017 there were.
Yeah, I think I saw that was in mountain region.
Yeah.
We do have a strict, as Dr. mentioned, we have strict policy to have a time speed of all these measurements for the 10 years. That's their baseline. And we do have a couple of locations in India, and of course Mukteshwar at the higher altitude, FMI and Delhi made the measurements, but it was around 9 years. So with the lack of 1 year, it is not really clear.
I see. Okay. Thank you.
Yeah.
For the nice talk. I have a question in this and next slide. Hey, it's just whatever you were showing, yes. So here you are showing this forest mixed, pristine, rural and urban.
Yep.
But if you see the absorption, means your mixed has lower absorption than the pristine side.
Yeah, it can happen. It can happen.
So means I could not follow this. Why is it so?
Well, there are some sites that are, let's say, for example, Jungfraujoch. This is a mountain site. So in that sense, it is there as a mixed, because it can experience both kind of conditions. As you can see there in the mixed site, it has very large variability in the rate. But mountain sites typically have lower concentrations because they're in the free troposphere often.
Even lower than the pristine sites, whatever it
yes.
is.
Yes.
Okay, so last question from Dr. Saran.
So, means I'm still more. I thought this is still more complex than simplified thing.
Oh, sorry.
So I have a simple theoretical question. Like, so we are seeing that CCN is activation is decreasing, and in the last slide, I think you hinted about new particle formation, forming CCN and then clouds. So means simple question, like which we have discussing since yesterday also, like this new particle formation, how much or what is the percentage that we know CCN can increase, but up to number cloud droplet number, how much percentage contribution you believe that this NPFs can reach at a climatic scale, not instantaneous?
Yeah.
That's what coming to my mind. You can comment just.
It's an excellent question and worth for a follow-up study for sure. At this moment we are still submitting this long-term CCN, but for sure the next step would be to quantify how much of that is from new particle formation. Thanks for the comment.
Okay, thank you, Dr. Antti. Nice presentation. So we'll have now the 3 lightning talks. Yeah.
Okay, thank you, Professor Day, for chairing the session. Let's first congratulate all the poster selectee. Out of those, only 3 will get chance for give a presentation. I'm sorry I forgot to do that earlier. So we'll go ahead with M. Deva Prasad. Yeah. Yeah, so you have 5 minutes exactly.
Okay. First of all, thank you, organizing committee, for selecting my abstract, and the judges for giving me option to give a post and talk here. So I am a PhD student from PRL. I am working with Professor Neeraj Rastogi, and this is a part of my PhD. I am basically working on carbonaceous aerosol to understand the sources, what are the sources of carbonaceous aerosol and the processes that are happening to this formation. So I during 2020 and winter to summer, like November 2020 to June 2021, I collected PM 2.5 samples from Ahmedabad and to understand the carbonaceous aerosol characteristics. So what the main focus I'm doing is I'm using carbon isotopes. That is, carbon has 3 isotopes, 12C, 13C and 14C. And that this 14C, it is radiogenic. So using 14C, we can tell how much of the carbonaceous aerosol is like coming from fossil sources and non-fossil sources. So I'm using 14C to estimate the contribution of that, and 13C, delta 13C, the determination. This is mostly used in like a geochemistry, geochemistry and all to understand the processes affecting. So in carbonaceous aerosol also we can use the processes affecting to the carbonaceous aerosol. So this is the time series of both concentration of PM 2.5 and this axis, which is F bio. F bio means percentage of carbonaceous aerosol coming from biomass burning or biogenic sources. So if you see here, like around 65% of the carbonaceous aerosol during winter, post-monsoon and winter is from biomass or biogenic sources. And when it is coming to the summer, it is reducing to around 45% in Ahmedabad. Here in Ahmedabad, like PM 2.5 concentration is like 100 to 94, like 82, and 35 during like a post-monsoon, winter, and spring and summer. Most of the time it is like more than 60 microgram per meter cube. That is like an average National Ambient Air Quality Standard. And in a post-monsoon, winter and summer, this is mainly like, what carbonaceous aerosol contributing more, and in summer, mostly water-soluble ionic species, mostly sulfates are contributing more in PM 2.5. And this is a correlation plot. This radiocarbon derived F by O, I correlated with some other biomass burning traces, that is potassium, and BC 370 by 880 ratio. It's not much clear here. So we are getting good correlation, and this slope we compared with our previous study, that is we did the radiocarbon measurement and this potassium and BC 370 measurements in Patiala. That was like a biomass burning time and mostly paddy residue burning, but there mostly the carbonaceous aerosol are primary. But in Ahmedabad, this is mostly secondary. So the slope is nearly 6 times lower in Ahmedabad. That's it, that in Ahmedabad, rather than primary, most are secondary sources. So to understand that, I plotted both the F by O, radiocarbon F by O, and delta 13C. 13C tells the processes that undergone. So I see here, like in this, like if you see here, these are mostly winter samples. Winter samples have mostly 65% of biomass derived carbonaceous aerosol, which have a very varying delta 13C value. This is like a minus 26 to around minus 25. That means like whatever carbonaceous aerosol reaching in Ahmedabad, they are mostly oxidized. So if you see in this, like here, this during winter the air masses are mostly transported from this IGP to Ahmedabad, and it is going to the Arabian Sea. So when I check the back trajectory, most of the carbonaceous aerosol coming from this, like here you can see the high AOD also coming transported from here. So that is causing this aging of the carbonaceous aerosol in summer. So that is supported by this WSOCB-OC ratio also, this color, and this it's a circle size shows the F44 fraction. F44 fraction that we got from the offline AMS analysis. So okay, offline AMS analysis, and so and similarly in summer we have depleted delta 13C around minus 27. And because here fossil fraction is like biomass concentration is 45 to 55%. So there also we are getting significant WSOCB-OC concentration and a lower F44 fraction. That means like in summer, like secondary organ terrestrial formation, that is also dominating. That is shown here. So summer is like Ahmedabad is a highly polluted environment, and carbonaceous aerosol mostly contributing in winter, post-monsoon and spring, and summer it is mostly like water-soluble ionic species. And this correlation in the absence of radiocarbon measurement, this potassium and BC 370 by 880 ratio, those people are already using, that we are supporting with our study. And in Ahmedabad also, like this oxidized aerosol and primary aerosol, like in Ahmedabad there is a variable sources of carbonaceous aerosol. These are the summary. Thank you.
Next,
Okay, so yeah, good afternoon. First of all, thank you all the selection committee and conveners for selecting my poster. So my name is Arun. I'm coming from IIT Madras, and I have been doing a research on understanding how aerosol loading is having an impact on the fog layer. So each year over the IGP, the news headlines goes up saying that there is huge disruptions in the day-to-day lives, and this is mainly caused by the fog layer that forms because of the regional meteorology. Now there is a general consensus that the aerosol loading is also increasing at this point, but to what extent does this fog occurrence is changing, or to what extent does the aerosol influences this fog occurrences have not been attempted before. So here what we do is, if you take a typical fog layer that you see from MODIS and you take a cross section along this line, what the calypso sees is that there is a clear demarcation between the fog layer and an aerosol loading lying right above it. So from these profiles, what I do is that I isolate the fog layer by simply giving a distinct identification factor that the base of this fog is touching the surface. And using that criteria, what we get is that most of the samples of the cloud samples that I got by giving this criteria was that the top height was between 0.2 to 0.8 kilometers. Within this, this fog layer is also accompanied by this aerosol loading laying above, and I just I find out the AOD as well. To understand how this AOD affects the top height, what we do is we simply see a regression, we plot a regression plot. Okay, 1 second. Okay, so yeah, what we find is that the top height is increasing by about 40 to 42% as the aerosol loading above the fog is also increasing. In general, what happens is that when there is a high amount of aerosols lying above the fog, the top extent increases from 0.4 to 0.6. The percentage of occurrences increases, while shallow fog does not. They tend to reduce. So to understand why these kind of things are happening is that we did a set of WRF-Chem simulations. First of all, we were able to couple the chemistry for the first time with WRF, and were able to simulate fog for the first time. And this shows the 3-day averaged fog top height, which is very well matching with the observed quantities. And did a set of sensitivity experiments to understand the changes in the fog top height as the aerosol loading changes. What we find is that there is a clear acceptance with the observation. We find that there is a top height increasing by 0.1 to 0.15 kilometers as the aerosol loading has increased. Now, these are actually preliminary results, and we are in preparation of a new manuscript that includes all the information of what model we have chosen and how the what parameterization combinations that we have done. And that's all. Thank you.
So good afternoon all. My name is Subrata Mukherjee. So I am working at IITM under Dr. G. Pandithurai. So my title of my presentation is like estimation of aerosol volatility and associated chemical characteristics, change in associated chemical characteristics over an high altitude forested site at Mahabaleshwar in Western Ghats, India. So like why this volatility is important? Because volatility is one of the important physical parameters that determines whether that organics and inorganic species will be in gaseous phase or in the aerosol phase. And we know that organics and sulfates are the most contributor in terms of submicron aerosol range, because submicron aerosols are very important because it contributes to aerosol in terms of numbers more. And we know that numbers are more important because it will eventually contribute to a CCN and hence cloud formations. So because we need to know this volatility, because this volatility will add more uncertainties in predicting ambient aerosols. If we want to model, so it will add more uncertainties and biases into the model if we don't know the volatility. So with that background, I have posed two objectives. So I wanted to find the volatility of different chemical species in submicron aerosol range, and I try to see more insights of these chemical species, mostly in organics, because it is contributing more than 60%. So in order to do that, actually what I have done, I have set up one experiment like combining thermal denuder system. So which thermal denuder system is a system we can set some defined temperature at high temperature, and I have coupled this thermal denuder system with high resolution time of flight aerosol mass spectrometer and with the SMPS. So HRT of AMS is giving chemical compositions, and this SMPS will give us size distribution. So I have two lines with a switching valve of 10 minutes. So one will be directly sampling ambient airs, one will be through the denuded air. And for denuded air, I've kept the temperature at 150 degree just to see how much volatility, like volatile species are there. Okay, so in terms of results, if we see actually, for organics, the extent of volatility is around 54%, and the maximum volatility I've seen for inorganic species, mostly nitrate, it is about like 18%, followed by ammonium, it is about like 60%, and the lowest volatility was seen for sulfate, because sulfate being the least volatile ones, it will tend to remain in the aerosol phase. So in terms of percentage of contributions, so organics reduced from 7% to 41%, and the sulfate enhanced from 33% to 47%. So in the course of denuded samples. So we also try to see whether whatever measurements we are doing, ambient and volatility, whether it's comparable within our atmospheric range, whatever is reported in literature. So we try to plot this fraction of 44 by 43 and try to see whether it is in the defined range or not. And we found out that it is in the defined range. And we have also tried to see whatever molecular markers are there, like hydrocarbons, we know that it is more volatile ones as compared to oxygenated ones. So, but what we found out basically, the hydrocarbons are having similar volatilities as of oxygenated ones. So we tried to dig into further more. For that, actually, what we did positive nitrate factorization. It is a technique, statistical technique to identify different sources, and we found out almost 4 sources, including HOA, BBOA, semi-volatile ones, and low volatile oxygenated organic aerosols. So HOA and BBOA being the more hydrocarbon-like ones, it should have more volatility as compared to other two, like SBOA or LBOA. But interestingly, what we found out basically, we found out SBOAs are more getting evaporated in the course of boiling as compared to HOA and BBOA. So we try to make one hypothesis out of it, because the experiment I have set up in winter season, so the air mass is mostly coming from the land origins. So it will be mostly laden with the emissions in course of its transport towards our observation site. So there will be lot of SBOA generation, and eventually it will be coated onto the pre-existing aerosols. So that's why we may be getting this kind of SBOA are getting more evaporated as compared to a BBOA or HOA. So in that course, actually, I want to emphasize that the processing of atmospheric processing of these organic aerosols into the form of SVOA can modulate these aerosol properties, and it can in turn affect CCN abilities also. So thank you.
Looks like we have to wait for food for some time. There is a protest going on outside by students, and they are not yet allowing, right? 5 minutes? Oh, perfect. Great. Thank you. Good news. Yeah, we are getting food. So we'll stop now for lunch. It's already 10 past 1. We have next session starting at 2 o'clock. So probably this would be, I think, quickest lunch that we can have. Maybe 40 minutes or 45 minutes, if you could. After food come. Yeah. Food is on the way. Yeah. So we can leave for lunch. Yeah. Rakesh?
Nano 2023, Vijay modified, the second one, last one.